microfoon. En zo klinkt het dus op het moment dat je
look for the remote. Yeah, so nice for you to be here. As Bas said, my presentation will be on the paper I've written about my master thesis. It's called "The Effect of Chordwise Deformation on Steady Aerodynamic Mechanisms in Hovering Flapping Flight." Wrong remote. So, yeah, just let me. Oh, okay. So, well, okay.
I'm sorry.
Yeah, can the lights go back out? Yeah, thanks. Okay, so this will be the overview of my presentation. First, I will clarify what I mean with unsteady aerodynamic mechanisms, because I'm not sure everyone's familiar with the term. Then I will tell about the goal of this study. I will show you the setup of my numerical simulations, and then some results and conclusions. So, unsteady aerodynamic mechanisms, like Bas already mentioned, the aerodynamics of flapping wings are quite different from those used in fixed wing aircraft or rotorcraft. For that matter, instead, they rely on unsteady aerodynamic mechanisms for the generations of their lift. Now, there are three important mechanisms I like to point out and quickly discuss. Those are the stable leading edge vortex, wake interaction, and clap and fling. Now, there are several others, however, I'm not going to go into detail about those. So first, let me quickly discuss stable leading edge vortex. What happens when a wing at high angle of attack starts to translate? You can see in the top left, when it starts to move to the right, flow will separate near the leading edge, and it will retach somewhere along the wing, creating a leading edge vortex. Now, when this happens in an ordinary wing, this vortex will grow, temporarily creating a large low pressure region on top of the wing, creating high lift. However, if the wing continues to move, this vortex will shed, resulting in a loss of lift or stall of the wing. However, what we see in, for example, flapping insect wings is that this same vortex is created and it remains attached to the wing, creating very high lift on the flapping wing. So this is a very important lift generating mechanisms in flapping wings. Second, wake interaction. Well, inherent to flapping flight is that, especially when you're in hover, the wing constantly moves through the wake left by the previous stroke. Now, this can have both positive and negative effects on the generation of lift. And we have to see which one applies for this case. A quick example of how this would generate a positive effect on the lift. So here you can see again in the top left the wing moving to the right. With the leading edge vortex, then as the wing starts to prepare for the following stroke, it starts to rotate. Both the leading edge vortex and the trailing edge vortex shed. Since these are counter-rotating vortexes, the air in between them is accelerated, creating an extra flow and speed-up flow towards the wing, and this creates temporarily an increase in lift. And finally, there's clap and fling. These are actually two separate mechanisms. They just usually occur together, so they're mentioned in the same phrase. Clap is the first thing that occurs when the wings come together. You can see first the leading edges of the wing will come together, then the air, then when the rest of the wings come together, the air in between the wings is pushed down, pushed out. This creates a small upward jet, or a downward jet, and a small upward force. Afterwards, fling is when the wings come apart again. Now you see the leading edges go apart first. This creates a low pressure region in between the wings. This almost instantaneously creates leading edge vortexes, and like I said, these leading edge vortexes are very important for the generation of lift. So in this effect, it will increase the creation of lift. So the goal of this research is to investigate the effect of the chord deformation on this aerodynamic effect. And I want to do this to improve the understanding of the physics involved in flapping flight. So I'm not here to say this type of deformation is best for your wing or anything. I just want to improve the understanding, and designing better wings is up to you guys. Yeah, like Bas also mentioned, I'm going to use this doing a numerical simulation. This is because we can, in this way, we can get a nice 3D, three-dimensional overview of the entire flow field. And I will use a prescribed deformation for the wings. So let me show you the setup. First of all, I modeled a single wing as a flat plate with an aspect ratio of 2 and use a symmetry plane to mimic the second wing. The Reynolds number, based on the average tip velocity, is around 2000, and we have a flapping angle of 45 degrees. Now, if we don't do anything, this will look something like this, with the lift defined in negative z direction, that's up. As you can all see, this would not generate any lift, so I add deformation to this plate. First, I define 3 types of deformation. First is actually rigid pitching, that's just pitching around the leading edge. Then there's a case with the maximum deformation near the trailing edge, and a case with the maximum deformation near the center. So when I use maximum, so this is rigid pitching, but no pitching near the root of the wing, and maximum pitching near the tip of the wing, and a maximum angle of 30 degrees, and this will look like this. Then the deforming end case, I call this. It's a maximum deformation at the end. It's a quadratic deformation. And as you can see, this will increase the effective angle of attack near the leading edge, which will be important in the creation of a leading edge vortex. This will look like this. And finally, a case with the maximum deformation near the center. Again, quadratic. However, now you can see that the angle of attack near the leading edge is decreased compared to the rigid case, and this will look something like this. Good, so results. These are lift coefficients of one entire cycle, so that it starts with an outstroke and then an instroke. There's 2 peaks in lift. And the straight lines, those are the average lift coefficients. You can actually see from this that both the deforming cases create a slightly higher lift coefficient than the rigid case. However, I'm not particularly interested in the actual lift coefficient that's created. I'm interested in the unsteady aerodynamic effects. Now, the first of which was the leading edge vortex. So let's first look at that. This can be clearly distinct from the start of the outstroke. Here you can see the green line, that's the deforming end case, and it has the fastest buildup in lift, and the deforming center case has the slowest buildup in lift. Now this has to do with the decreased angle of attack or the increased angle of attack near the leading edge. So on the bottom I have plotted Q criterion, which is a good indicator of the vortex. In the middle, you see the deforming end case. You see a much stronger leading edge vortex near the leading edge compared to the other 2 cases. And in fact, this higher angle of attack instantaneously creates, or not instantaneously, but starts creating a strong leading edge vortex almost right away, resulting in a much stronger buildup of the lift coefficient. This in the next time step, you can see the leading edge vortex of the deforming end case grows much faster compared to the other 2 cases. Now, another interesting thing to note is there are clear humps in the lift buildup. You can especially see that in the second peak during the in-stroke. You see clearly lift buildup and then a hump in it. Now, like I said, leading edge vortex stability is very important and one of the main generators of lift in flapping wings. So if we see such a hump, it's quite natural to assume that this leading edge vortex has shed. So let's see if this indeed happened. Well, these humps are clearest during the second peak, during the in-stroke. So let's look at that first for the deforming end case. Here I've plotted again Q criterion on these 3 crosses. You can see during the lift buildup. Now, it's hard to point, but the leading edge vortex is actually, so the wing is moving to the right. So the leading edge vortex is behind the wing. And you can see it moves down a little bit along the wing. However, if you compare, for example, the middle one and the one on the right, then the lift starts to build again. And it's hard to explain it using just this leading edge vortex, because there doesn't seem to be some shedding going on between the first and second picture that isn't going on between the second and the third picture. So it's hard to actually get this from shedding of the leading edge vortex. And the same is true when we look at the rigid case. We see, again, a build-up now for the first 2 points, and then at the third one, you actually see a sudden decrease in lift. But we can't really explain this, again, from shedding of the leading edge vortex. So again, something else has to be responsible for this. So some of you may already have wondered, I know it's early, but some of you may have already wondered what this large vortex in front of the wing is. Well, that's actually the vortex shed from the previous stroke. And looking at the three-dimensional view of the flow field, we can clearly see what I'm talking about. This, so on the top is the start of the in-stroke. The wing will now move towards us. So this large, these are isosurfaces of the pressure, negative pressure. Like I said, vortex create low pressure regions. So plotting isosurface of negative pressure will show you these vortex structures. Now what you see in front of the wing is the vortex shed from the previous stroke. And in the deforming end case, you can see already at the top of the wing the new leading edge vortex starting to build. Then one time step later, we can actually see that the new leading edge vortex in the deforming end case starts to interact with the vortex from the previous stroke. So we get this interaction. And in fact, this moment in time corresponds to this hump in the lift buildup. Then if we continue, we can see that in the next step, this interaction is finished for the deforming end case, and in fact we see the lift rise again. Now for the rigid case, we now see this interaction, and again this corresponds to a hump in lift coefficient. And afterwards, when we see the lift rise again, indeed this interaction is finished. So we can see that a hump in the lift coefficient is in fact caused by interaction between the leading edge vortex and the vortex shed from the previous stroke. Now for the case where the deforming center case, which lowers the angle of attack near the leading edge, we don't see this interaction. And here you can clearly see why. Because the deformation that increases the angle of attack near leading edge, you can see, first of all, it's the leading edge vortex builds much faster, but also it pushes the vortex shed from the previous wake up towards the leading edge vortex. And then you can see in the deforming center case, actually the previous shed vortex is pushed below the wing, and the wing in fact shields the two vortices from each other, preventing this interaction, which is clearly beneficial because it prevents this hump in the lift buildup. Now, and just to be sure that indeed interaction between the previous shed wake and the new wake, and the new vortex is responsible for this hump, we check the initial stroke, because of course if you have the first stroke, then there's no previously shed vortex, so there shouldn't be any hump. And indeed, looking at the lift during an initial stroke, we don't see any humps. So indeed we can say this hump in the lift buildup is caused by the interaction between the new leading edge vortex and the previously shed vortex. Then the last aerodynamic mechanism I wanted to talk about is the clap and fling. I investigated this by first simulating a single wing and then moving a wing close to a symmetry plane. Now you don't have to completely make the wings touch to get the effect of clap and fling. You can in fact get that by moving it closer, and we can see this quite clear. Now I did this for the rigid case and the deforming center case, and from this picture you can see, although the distance from the leading edge to the symmetry plane is equal for both cases, due to the deformation in this deforming center case, you see that a larger part of the wing is near the symmetry plane. So we would expect the effect of clap and fling to be more pronounced for this deforming center case. So let's see if this is indeed the case. So this is for both the rigid wing and the deforming center case, the increase in average lift coefficient compared to a single wing. Now we see that when we move the wing to a distance of 0.5 chord length to the symmetry plane, in fact, for the rigid case, the average lift coefficient increases with 3.4%, whereas for the deforming center case, it increases 5.1%. So indeed, this increase is larger for the deforming center case, as we expect. However, when we move it even closer, you can see that the increase for the rigid case is actually 11.3%, and for the deforming center, only 9.2%. So now, instead of being larger for the deforming center case, it's larger for the rigid case, which is not what we would initially expect. Now, to see why this is the case, we can look at the lift coefficient. And what we can see here is that indeed a much stronger lift buildup due to the fling effect, the almost instantaneous buildup of the leading edge vortex. You can see faster lift buildup. However, this also causes this hump, this interaction between the new vortex and the previously set vortex to occur faster. Now you can see for the rigid case, this isn't as big a difference because this interaction was already quite strong and it just moves ahead. However, you can see for the deforming center case, this interaction happens way earlier, but it also takes a lot longer. And this is due to the shielding of the wing between the two vortices. It limits the interaction, but only after the interaction is complete can the lift start to build again. So in this case, the fact that the interaction is made so difficult actually hinders the lift buildup. So the effect of clap and fling is reduced. Now then, conclusions. When we have a deformation cause a higher angle of attack near the leading edge, this results in faster leading edge vortex buildup, and with this faster buildup of the lift coefficient. We didn't see any shedding of the leading edge vortex, which is very important. So in fact, increasing the angle of attack creates a strong leading edge vortex, but no shedding, so that's only beneficial for this case. However, what we did see is that interaction between the new leading edge vortex and the previous set vortex had a negative effect on the lift coefficient, and that we also saw that when the deformation causes a lower angle of attack near the leading edge, that this interaction takes longer, and so it is in fact beneficial to have a lower angle of attack because it limits this interaction. Now, as for clap and fling, we saw a clear beneficial effect on the lift coefficient and the lift buildup, and this was initially more pronounced in case deformation caused a larger part of the wing to be near the symmetry plane. However, we also saw that when they became too close, the interaction between the new leading edge vortex and the previously set vortex actually occurred much faster, and this limited the benefit of the clap and fling. That was my presentation. I hope you enjoyed it, and if you have any questions, feel free to ask.
Okay, the paper is open for questions. And if you have a question, Thijs, please repeat the question so that...
Yeah.
So, based on these conclusions, what could you say for the design? Let's say, how could you, of course, very practical question, how could you perhaps make it bend the way you think is most beneficial?
Okay, so the question is, how would you maybe implement these results into an existing design, or how would you make a design that benefits from these results? Well, to be honest, that's first of all, it's very difficult to say because these deformations usually flapping wings, they use a very flexible design, so to make them deform in such a way is non-trivial. Of course, you have to remember these are prescribed deformations. However, you can imagine, for example, if you want to simulate clap and fling, it will create a large low pressure region in between the wings. So if you have completely flexible wings, the shape will be influenced largely by this low pressure region. So to have pre-designed shape is rather difficult.
And the sensitivity, like to the parameters, so you took some parametric shape for example, the bending.
Yes.
How sensitive do you think your results are to the exact parameters? Suppose you make it slightly hollower or slightly, do you think it will have a large influence on the results?
Okay, so again, the question is how would the how sensitive are the shapes to these results?
The results to the shape.
Yeah, sorry, the results to the shapes. Yes. Well, the thing is, the things I tested are, for example, very important is the increase in angle of attack near the leading edge, and of course, if you have a higher angle of attack near the leading edge, it will speed up the creation of a leading edge vortex, speeding up the creation of lift. So this is, well, not very sensitive. If you increase the angle of attack, you will get a faster lift buildup, and if you decrease it slightly, you will get a slightly lower lift buildup. And so in that way, it isn't very sensitive to this at all. As for the clap and fling, it's really difficult to say because defining actual shapes in full clap and fling or near clap and fling is actually a lot more difficult than just prescribing the deformation. This was just this is more like a proof. If you could get the shape, this would happen. But to say anything about the sensitivity, it would be rather difficult. So I hope that answers your question. Okay, thanks. Yes, yes, you sure. Okay, yeah.
How useful is this study considering that practically used wings are not rectangular?
Well, so the question is how practical is the study if you consider that real wings are usually not rectangular? Well, the thing is, again, a large part of the study focuses on generation of the leading edge vortex and based on angle of attack near the leading edge. And even if the rest of the wing is a different shape, the generation of a leading edge vortex is always, it's the main lift generating mechanism in insect flapping wing flight. So this will be important no matter how what the shape of the wing, as long as it relies on generating a leading edge vortex for its lift. Got that? Yes, that answer. Yeah.
Thank you for your presentation. Can you go to slide 15?
15. Yes.
Yeah, if you look carefully at the dimensional time around 0.5, you
Yes.
have a little bit negative lift.
Yes.
How is it possible if you have a wing flap at inner fluid at rest, there will be always jet flow afterwards?
So how is it possible that we have negative lift?
Yes.
Well, the thing is, you have to imagine that the motion is entirely prescribed. So the wing actually, initially, the wing, of course, starts to move. Let me think of how that. So if this is your symmetry plane, the wing will move without any deformation like this, But if we add deformation, it will first move like this, and then. So if that's not timed perfectly, then you will get a bit of negative lift due to the deformation not being in sync with the actual motion of the flapping. Is that clear?
Yeah.
Okay. Yes.
There was a question there.
I want to thank you for an interesting talk. I'm not an aerodynamicist, so usually I get lost, but I didn't this time, so thank you for that.
Okay, great.
Then we have this figure here. I wanted to ask about the lift coefficient because we can see that it's not symmetric in downstroke and in upstroke.
Yes.
So I guess it's because you didn't simulate enough wing beats. So I wanted to ask how many wing beats you have to simulate to get something that would be symmetric. So you would have the lots.
No, as a matter of fact, the reason this is not symmetric is because I already used the symmetry plane. So this is a simulation with the symmetry plane at 0.5 to chord length. So in fact, the reason this is not symmetric is because the clap and the fling effect is already present, even for this case. Second interesting part about this is that because I also did single wing simulations, and then sometimes you might have see because I simulated, for example, 10 cycles, and then you can see that because this is hover, so for all the vortices, the wake, it of course builds up, and you can actually see that once in a while suddenly it interacts with the wake, and so it might never become fully periodic simply because it's hover. Does that answer your question?
Yes.
Okay, great, thank you.
One last question. If
No? Oh, yeah.
yeah.
When your vortex separated from the wing,
Yes?
did you find the separation starting from going from the rear of the wing or coming from the leading edge of the wing, or did you notice a difference on that?
So the question is, if when I witnessed vortex separation, did it start at the tip of the wing or the root of the wing?
No.
No, sorry.
At the leading edge
Yes.
or the trailing edge? Did it come from the trailing edge forward or the leading edge back, or some of both?
Okay, so whether it comes from the leading edge down or from the trailing edge up. Well, because you have to imagine, I presume you're talking about leading edge vortex, right? So when the flow will always separate near the leading edge first, and then it will return towards the core. So it will move like, so it will reattach somewhere along the wing. So separation will always occur when it no longer attaches, so it moves away from the wing. So you get, yeah, it's a shape similar to the one in the middle, actually, when you see the separation. However, like I mentioned, I didn't really see clear vortex separation, also because it's, of course, a complete two-dimensional shape, and you also have a tip vortex, so it isn't really clear. And like I mentioned, I didn't see clear vortex separation, so I couldn't really say. Hope this answers your question. Okay, great, thanks.
Okay, then let's thank the speaker again. And we move on to the second speaker. The second speaker.
And hi, good morning, everyone. The topic I'm going to present today is the vortex evolution and the fourth generation analysis on the flapping wing IMAV Delphi 2 in hovering flight. I'm here to present a paper on behalf of all the authors here, since I'm the fourth author in the list. And the first author is a master student, which was involved in our flapping wing experimental study from the University of Pisa in Italy. And as you can see, we have a lot of people from Asia, European, and Mid-Asia, so it's quite an international job here. And my name is Shuangho Deng. I can understand it's very difficult for the European people to pronounce my name, but I promise you my name will be the most difficult part in my presentation. let's go to the content first. And we have 4 parts here. First, I'll give you some brief introduction and the objectives of this research. And also the experiment setup will be discussed later on, followed with results and conclusion. I'm not going to talk too much about the Delphi ornithopters developed by TU Delft, since you have already quite familiar with this kind of flapping wing MAV. The first Delphi one was developed in 2005 that we kick off a new project aiming to develop the new generation of micro aircraft. And later on, we optimized Delphi 1 into Delphi 2, which you have already saw the demonstration on Tuesday in our flight arena. And it's the Delphi philosophy that keep minimizing the Delphi, but without sacrificing too much flight performance of the Delphi. That's why we have Delphi Micro built in 2007. The model for this experiment setup is Delphi 2. Okay, the overall objective of this such research is to address the aerodynamic performance of Delphi 2 in hover, the time-resolved fourth generation and the flow field topology on the wing and also in the wake of Delphi 2 in hover, also required by force balance and stereo PIV technologies. The vortex structure was also investigated and then linked to the force production. Also, three-dimensional wake structure of Delphi 2 in the wake will be reconstructed by Kriging interpolation technique. The effect of some important parameters, such as the flapping frequency, aspect ratio, and flapping frequency and aspect ratio will be evaluated on their force production and also the flow structures. Here is the experimental setup of the data acquisition system. Then we can see the Delphi is connected, is mounted on a force sensor. It's ATI Nano 17 titanium, which is I think it's the smallest force sensor, the commercial force sensor in the world, and it's very precise, can resolve the force down to 0.14 grams without any filtering. And the flapping frequency of the Delphi 2 is controlled by a combination the Hall sensor and also speed controller signals. The center one is the control board, which was built, I think, several years ago by Christoph from the IMAV lab. Later on, all the necessary information, that is the force in XYZ direction, and there are 3 moments. The current, the voltage directly fit to the Delphi 2 was acquired by a FPGA-based discordant system. In our measurement, the data recording frequency was set at 10,000 Hertz to guarantee we have enough data in one flapping cycle. This is the setup of the PIV, setup for the PIV measurement. We have the vacuum measurement to identify the inertial to aerodynamic effect, and also 3 different PIV setup to capture different position of the Delphi 2. I will give a detailed introduction later on. We first go to the vacuum test. The vacuum test was performed in our high-speed wind tunnel of the aerodynamic lab. The maximum Mach number is around 11, but we're definitely not going to use the blowing part. The Delphi 2 was mounted up and down since we have support from the top in the vacuum session, and the vacuum level is around 1 millibar. It's already near vacuum, and we think it's quite enough for identify the inertial to aerodynamic effect. This figure plots the power spectrum density of the thrust component, while the black and the red lines are the power spectrum of the Delphi in air and in vacuum respectively. As we can see, the first 2 flapping harmonics are really predominated by aerodynamics. That's why we decided later on to use a Chebyshev type 2 low-pass filter to filter the thrust, the current, and also the voltage by keep the 2 harmonics of the flapping frequency. And this one, we named it setup 1 to measuring the flow structure on the wing. That the laser is from the front of the Delphi 2 directly illuminate on the wing. The wing was painted black to. Yeah, this one's super. Okay. This wing was painted black to decrease the reflection of the laser. And also we have 3 cameras on different position of on the side of the Delphi 2. I think this third camera, we use the middle one and this one for the stereo PIV, and this one is for the backup. If we lose some information there, we can find it from this third camera. During each case, the 6 images are captured by a 300 recording frequency, a double frame recording frequency of the camera, to guarantee we have enough flopping cycles for the later ensemble averaging. Also, a CFX fork generator will generate the water glycol-based particles with a mean diameter around 1 micrometers as the tracing particles. In the post-processing, the LaVision David 8.2 was used. And also, in the measurement, we used the LaVision Type 30 calibration plate to calibration in the first. And also, later on, we used self-calibration to correct the misalignment between the laser sheet and also the measurement plate. In the post-processing, we used the image integration was performed by multi-pass stereo cross correlation. As we can see, first measurement, the field of interest is around 21 centimeter by 21 centimeters, and the different position of the laser sheet from the 2 centimeters from the root and until, I think it's until 16 centimeters outside the wing. The second setup that is aiming to measure the force, measure the wick topology along the streamwise. Also, we use this 22 by 22 centimeter field of interest and the same position here. At the second setup, we measure the wick topology along this spanwise position. It's from 1 centimeters after the wing until 21 centimeters in the back. Well, about fourth generation of the Delphi 2, here we plot 2 periods of flopping cycles. The green line here is the phase angle of the upper wing of the Delphi. We can see it's not really perfectly symmetric between the in-stock and out-stock, which we think is the interaction between the wing to wing during flap. It needs more time to peel. And also, we look at this is the thrust generation. We have 2 thrust peaks involved in one flopping cycle. The higher one occurs at the outstock, is after the middle of the peel, and the lower one is at the middle of the in-stock. Now, this image is from the setup 1, is on wing measurement. This black period is due to the laser sheet is blocked by this wing, but still we can have some useful information from this one. Here we have 2 counter-rotating vertex pairs, which is generated by the previous clap motion. And here, also another pair of counter-rotating vertex are going to shed at the trailing edge. Here the angle attack is very slow. That's why we have this very small thrust generation. When we move back, this 2 vertex is already shed from the trailing edge, and since it's hovering case, that means it's without coming free stream velocity. This 2 vertices is quite stable to stand here. When we keep going back, it's at the beginning of the outstock. That this 2 shedding vertex from the trailing edge travels so slowly because there is no wind speed. And this two counter-rotating pair is going to be disappeared going on. Then we can see a huge vortex pairs on both upper wing and lower wings that bring a much more suction part on the wing. That's why we have a peak here for the thrust. Also, it's going on here that the vortex is starting to paving around the wing. It brings more thrust also. Here we have second one that we can see the shading of these two vortex. Also 7, 8 different. It's quite a complex vortex structure. Yeah, this a weak measurement result is from the setup tool that we put the laser sheet along the streamwise after the Delphi wing. Then we can see the shading of this vortex pairs alternately generated when it flap. The top one is the outstroke, and then the bottom one is the in-stroke phase. I'll show you a video here to see. It might be much more clear. That during the flapping, that's the vortex, the counter vortex pair was shedding alternately by in the outstroke and also in the in-stroke. We can see a clearly jet flow structure here. That's because of the flapping wing and also enhanced by the induced velocity of the counter-rotating vortex pair. Later on, we use a 3D topology Kriging regressive with local area estimation to reconstruction the 3D weak topology after Delphi wing. Here we have this Kriging interpolation function in Bayes framework. The advantage by using the Kriging is we can work with abstract data, and also by coupling the local error estimation, we can incorporate the measurement uncertainty in this interpolation. In our measurement, the signal-to-noise ratio in stereo PIV was used as the error input, and also we used frequency domain sample variograms to limit the computational cost. By performing Kriging interpolation from the data of setup 2, then we get this structure here. You can see this is an in-stroke structure, which was shed after the in-stroke. And here we have this one. It's not really clear. It's like arc shape, which is shed from the previous outstroke. And also here is a movie about the shedding of the vortex. Now we can see there are 3 predominant swirling vortex structure. Which here we name it U-shape. It's the in-stroke structure shed from the wing. And here we have the outstroke, this arc shape shed in the outstroke. And later on, we also evaluate the effect of wing aspect ratio. The standard wing we named here as TD is the normal wing on Delphi 2 with 140 millimeters, have a half wingspan. And we keep this one, keep the core length stay the same, and also the tip length stay the same. We only increase the span wise from 40 centimeter to 16, then back to 12. The harder means the high aspect ratio with different error as an abbreviation. Then we can see the force generator here is also plot in 2 cycles. Then we can see from this graph, the higher aspect ratio, the higher span wise result in a higher thrust generation, and they are quite in phase. Only a small shift here, which might due to different acceleration level of the wing. Also, this 3 flow structure from the on-wing measurement of different wing is shown here. We can see the structure topology is quite the same, only different in the magnitude. Besides of Delphi 2, we also did some measurement on Delphi micro with SIM setup. Delphi 2, we only measure the half of the Delphi since we assume it's a symmetric configuration. But for Delphi 2, we have a top collapse and fling. That will result a symmetry, not a symmetry. It will result a complex vortex structure. And from here, we also reveal this U shape shed by the clap of the wing in the end of in-stroke, and also this arc shape shed due to the outstroke. The flow topology of Delphi micro is quite the same as Delphi 2. Here is for different phase. And also, we also compare the different flapping frequency and the different wing aspect ratio. They are nearly the same flow topology, but only different in magnitude. Also, it's time to wrap up this research. That two thrust peaks different in magnitude was present in each flapping cycle. The lower one happens at the mid-in-stroke phase, while the higher one occurs at the beginning of outstroke. But in Delphi micro, it's the opposite way. The higher one happens during the in-stroke, and lower one in outstroke. And the first two harmonics, the fourth spectrum, are aerodynamically related by the vacuum test. The leading edge vortex developed during the hovering flight with Delphi have been confirmed to be more major aerodynamic feature that allow Delphi to stay aloft, as well as flexibility of the wing. The fling has for Delphi 2 only, the fling has the fundamental role of creating an inrush of air between the wing and thus enhance the generation of the leading edge vortexes. By the 3D reconstruction of the wake of Delphi 2, we find two very predominant vortex structure, a U shape and a knock shape, happens during in-stroke and outstroke, respectively. Well, the effect of the flapping frequency and the wingspan, the different flapping frequency and wingspan also give the similar flow topology. They are only different in magnitude. And the higher frequency and the aspect ratio will just produce a stronger vortex structure, but they can bring more thrust. And yeah. Okay, thank you. And
questions?
yes?
Very interesting presentation.
Mm-hmm.
Your name is not because.
Yeah.
My question is regarding the vacuum test.
Mm-hmm.
The wing do not deform the same way in vacuum.
No, it's quite different. It's quite like a waving
Shuangwu,
shape.
can you repeat the question for the...
Okay, so your question is, in the vacuum test, the wing didn't deform at the same way as in air.
Yeah. Is that a good representation of the whatever that you measure in vacuum? Is it you're trying to minus off the inertial part of the measurement, right?
Yeah.
So is that still a good representation of the real flying condition?
Yes, I think so. And the vacuum test for us is only to identify the difference between the aerodynamic effect and also the inertial.
So it's not used for a correction,
No.
but it's just used to see which harmonics are certainly not related to inertia effects.
Yeah.
Other questions?
You mentioned about the creaking thing. Is that just to reconstruct the wing?
Yeah. Yeah. Yeah.
Isn't it more simple than just build up and then just need to go to that filter because it's dissipative?
The question is, in the creaking interpolation is used for reconstruct the wake, but why just use different plane and?
My knowledge that algorithm is very dissipative. That means you're going to lose all the small scale.
Yeah, for sure. By creaking, we definitely will get rid of some small structures, and there is also smooth function inside the creaking. That is, as we see it, we also use the temporal integration based on the Taylor's hypothesis. That means we use only one measurement plan and different time to interpolation. That from the results we found, it's quite the same. So we think the quick interpolation is quite acceptable in our measurement.
There was a question in the front.
Oh, sorry.
During your experiment in the vacuum, what was the frequency of the wings?
The wings we tested from 10, 11, 12 until 14. That one is 12 hertz. Yes, they all give the same story. The first two harmonics is predominated by the aerodynamic. The rest from third is purely, it's not purely, it's less affected by the inertial.
And one more question.
Mm-hmm.
In your experimental setup, how was the area of interest decided upon? You had 21 centimeter by 21 centimeter. How was that decided upon?
The wing flap is around, the wing length is around 14, the half span, and we can only capture the half of the wing since it's a symmetric mechanism. And 21 we decide it's, I think it's already 7 centimeters away from the wing, and we think that might be quite enough. But also in the post-processing, we didn't find any structures involved in like 20 centimeters. That we also see the results directly after the measurement. If there's some like chaotic flow there, then we will increase the size, but fortunately we didn't find that one. Yeah.
There's a question up there.
Yeah.
For the force measurement or diffraction that you have showed, did you use some filtering, or are those the raw data that you measured?
I will repeat the question since you said in our force measurement if I use the filtering function or not. Yes, we definitely use the Chebyshev 2 low-pass filter.
Okay.
Yeah.
What was the cut-off frequency?
The cut frequency is we keep the first two harmonics since it's aerodynamically related. And after that, we just cut off all of them. Yeah.
I think then this brings us to the end of the presentation. Let's thank the speaker again.
Thank you very much.
And we're nicely back on schedule. I don't know if Guido wants to give some extra comments.
Just coffee.
If not, we can hit the coffee.
May I begin? Great. Well, thank you everybody for coming. My name is Mark Jankowski. I'm very excited to be here today. I'm going to be discussing a little bit about the research I've been working on for about the last year and a half, and that's regarding dynamic modeling of a rotating insect wing. So first, I'd like to begin with an outline of the presentation, a little bit of motivation. First, why we believe there is some amount of utility to this model, and really how we feel it's unique from some of the existing models. Then I'll step through the model formulation, ultimately how we developed this model of a rotating insect wing, after which I'll apply it to the forewing of a Manduca exsexta, which is kind of the classic flying insect, also known as a hawk moth. After that, we'll look at a couple of the key results that we found, and I'll briefly conclude the presentation with just a brief summary of the results. So first, let's talk a little bit about the motivation, why we started this research. Obviously, the study of flapping wing research has a lot of applications in both engineering and biology. So for engineering, flying insects often tend to serve as the paradigm for small flapping wing style microaerial vehicles. And this is because they're really capable of doing kind of evasive maneuvers while maintaining this robust stability. So for biologists, this research provides insight into the sensory motor coordination of insects. So some of you might know that insect wings are richly imbued with what we call mechanosensation cells, which from an engineering standpoint really behave similarly to something like a strain gauge. And it's believed that a large amount of the neural feedback that an insect receives during flight is generated through the strain in these, basically in these cells. And it's our belief that if we're able to basically model this and interpret this in a similar way to an actual flying insect, this might facilitate designing control systems for small flapping wing microaerial vehicles moving forth. So prior to beginning this research, we did a brief literature review just to kind of see what models were available. And we found that there's several unique models out there, but they generally fell into one of two categories. And this was either the rigid body model or the finite element model. So the rigid body model treats the wing as a single rigid, undeformable structure, and really has a number of benefits associated with this. The first is that it retains a low number of degrees of freedom. The benefit to this is if you're trying to do something like a parametric study, the computational time required to solve something like this is very, very small. Furthermore, if you treat aerodynamic forces as forces, kind of as generalized forces acting on the wing, you can predict some of these aerodynamic parameters, such as lift and drag, which are of course of interest to people that are designing microaerial vehicles. But kind of the disadvantage to such a model is that you're unable to really estimate the localized strains that are developed within the wing during flight. So obviously these models have limitations in terms of biological studies of the neural feedback an actual insect is receiving. So the other subset of models then is the finite element model. Now the finite element model is of course capable of predicting these localized strains, but unfortunately it's only really capable of describing infinitesimal rotation, which of course has limitations as the rotations of an actual insect tend to be very, very large. Should you try to include these large rotations directly in finite element modeling, the result will be a time-varying stiffness matrix. So basically, this stiffness matrix must be updated at every single time step during your finite element analysis. And the result of this is an enormous amount of degrees of freedom, basically making a direct finite element approach computationally infeasible. So the aim of the proposed research then, shown in blue here, is to really synthesize the benefits of each of these two subsets of models into one comprehensive dynamic model of a rotating insect wing. And we'd like this to have the following three important characteristics. One, we'd like this to remain or have a low number of degrees of freedom, such that we maintain this computational practicality. Second, we'd like to be able to predict the localized strain in the wing, such that we can use such a model for the insect neural feedback studies. Third, we'd like it to be able to accommodate arbitrary geometry. And what I mean by that is I'd like this to be able to be applied to not just the forewing of a hawk moth, but rather anything that flaps its wings. So before talking about how the model is developed, I'll mention the assumptions that are made. First, we've assumed that the in-plane deformation is small. So all the elastic deformation is assumed to be out of plane. Second, we're going to assume that the deformation of the wing is entirely a result of inertial elastic effects. So we'll be neglecting some of the aerodynamic effects that a lot of the other researchers have been presenting here during this conference. So now that I've kind of spoken about the motivation behind this research, I'd like to talk about how the model was formulated. So the first thing that we've done is basically treat the insect wing as a deformable body subject to three-dimensional rotation about a fixed point on the insect's body. And this is really where the forewing meets the body, as you can see here. And so we've established two finite rotations, roll, which we've called alpha, and pitch, what we call beta, to establish a rotating reference frame that rotates with kind of the dominant rotations of this wing. And how this is set up is basically we've set this in the standard IJK kind of coordinate frame. We perform the roll rotation about this axis here, which transforms us to what we call the prime coordinate frame. Then we apply the pitch about the J prime axis, and that kind of transforms us into this last coordinate frame then, which is the double prime coordinate frame, which we'll use throughout the remainder of this formulation. And some basic geometric analysis then shows that the angular velocity is this expression on the lower left-hand side. So the third rotation that we've implemented then is this yaw rotation, which I've unfortunately forgot to draw on the figure, but this is going to occur about the K double prime axis here. And basically, this will not be considered in the rotating reference frame. It's considered very small. And what this basically allows for it to happen is the wing can really yaw within the rotating reference frame. So now that we've established this rotating reference frame, I would like to draw a position vector to some differential mass element, which will ultimately be integrated over the entire mass domain of this wing structure. And this is really comprised of three intermediate position vectors. Position vector R1 then is the planar position of the differential mass element without regards to the yaw rotation. So then vector R2 basically considers the infinitesimal yaw rotation. And again, we're considering this to be small, so we've employed some small angle approximations here. And the last and probably the most interesting position vector then is R3. And this is representing the infinitesimal out-of-plane elastic deformation of the wing. And this is contingent on both position and time. So essentially what we've done here is we've superimposed an elastic deformation on top of the large rigid body motion of the wing. And of course, you can sum these three vectors to give you the total position of the differential mass as a function of time. Okay, so I don't want to get too much into the mathematical detail here, but I'll point out a couple major features as to how the model was developed. And in my opinion, the single most important feature is the eigenfunction decomposition of the elastic deformation. So ultimately what we're doing here is we're decoupling the time and position dependence. And the benefit to such a decomposition is that we're able to find the position dependence entirely through finite element. And this is called the mode shape, which we've denoted by the letter phi. So really the only remaining variable to fully characterize the dynamics of this rotating wing is the modal response, which we've denoted by the letter qk. And really that's just the time response of one of these mode shapes. So to formulate the equation of motion that governs these modal responses, we've basically come up with expressions for the kinetic energy, indicated by T, and the potential energy, indicated by V. And we'll use Lagrange's equation with these energy quantities to essentially figure out what the equation of motion for the kth mode shape is. We've also defined two vector quantities here which relate to the inertial force center. The only reason I've presented these is because they'll show up in the equation of motion. So after applying Lagrange's equation, we've ultimately found that this is the equation that represents the time response of the kth mode shape, or when solved, represents the time response of the kth mode shape. And so you'll notice two important characteristics of this equation. First, it's time varying. And the time variance is introduced through the stiffness term. So this is kind of a meaningful result because the average stiffness over a single wing beat will actually be a little bit lower than the natural frequency of the same static wing. So this basically reduces the natural frequency slightly. The second meaningful result then is that it's linear. And what this allows us to do is really look at each response subject to each excitation term individually. So we can kind of decouple some of these excitation terms. So what are the excitation terms then? We've identified 3 that are common within a rotating reference frame, and that is the Euler force, which is really just due to the acceleration of this coordinate frame, the centrifugal force, which tends to draw the body away from the center of rotation, and lastly, the Coriolis force, also called the gyroscopic force. And this occurs when there's relative motion happening within a rotating reference frame. And in this case, that relative motion occurs because of the yaw rotation, which was, again, predicted as, or assumed to be small. So now that I've formulated this model, I'd like to apply it to, or I'd like to show you how to apply it. And to do so, we've basically dreamt up an example wing that's similar to that of the forewing of a hawk-moth Manduca sexta. Now, I'd like to emphasize the point here was the goal was not to perfectly emulate this wing, but to rather capture a couple of the essential characteristics, namely the first few natural frequencies. So how we basically dreamt up this wing was we traced CT images of an actual hawk-moth wing in finite element, or Abacus finite element software. We replaced the membrane material with a paper material of uniform thickness, and we've neglected the venation pattern. We've also implemented a camber geometry with about 13%, which is certainly exaggerated from that of a real insect. And we notice that this has the effect of lending support to the first bending mode. So really what you're doing is you're increasing the natural frequency without changing the mass or altering the actual stiffness properties of that wing. And what we found was our finite element model, really despite all these simplifications, estimates the reported values of an actual hawk-moth wing within about 5%. And you'll notice the values here are about 63 and 87 hertz, and those numbers will become an important factor in a couple minutes here. And this image here shows the mode shapes of the first 2 modes. This is the first mode, which is a bending mode, and this is the second mode, which is a twisting mode. So for this example, we'll just consider these first 2 mode shapes. So the next thing that we'll do is assume some rotation profiles. So the formulation basically can accommodate arbitrary rotations, but for sake of simplicity, we'll assume that they're harmonic and in phase at this time. So these are the rotation amplitudes for an insect in forward flight at about 5 meters per second. This is just taken from the literature, and certainly you can use any rotation amplitudes that you'd like. And the driving frequency that we've used is 25 hertz, which is consistent with that of an actual hawk moth in both forward flight and hovering flight. So now we'll take a look at some of the excitation terms, or really all of the time-varying terms in this equation. And kind of the important feature that we'd like to look at here is the frequency content associated with each time-varying parameter. So as I mentioned earlier, the stiffness is time-varying as a result of this centrifugal softening effect. And we found that that actually occurs at about twice the driving frequency of the wing, or twice the flap frequency. The Euler force oscillates at about the driving frequency and has depreciating superharmonics at twice the driving frequency, 3 times the driving frequency, etc. Perhaps the most interesting result we found here then is the gyroscopic force, or the Coriolis force, which oscillates at exactly twice the driving frequency. And this value actually falls very close to the first natural frequency of the wing, indicating that there might be some amount of resonance activated here. And furthermore, this actually occurs kind of in sync with the stiffness term, meaning when the Coriolis force is at a maximum, the stiffness is at a minimum. So that's kind of an interesting result, as you're kind of pushing harder as this thing is softer. And lastly, we found that the centrifugal force oscillates at the driving frequency and 3 times the driving frequency, where 3 times the driving frequency is falling near the second natural frequency of this. So again, we kind of have these resonance effects now in the first 2 structural modes of this wing. So this slide here will show the modal responses simply for the first mode shape. I've not shown the second mode here. You'll notice that the Coriolis force generates the largest response, and that's, again, because we're operating kind of near this resonance point. The centrifugal force, then, which is not shown, is, for the same reason, generating the largest response within the second mode shape. And interestingly, because of the proximity of the forced vibration and the free vibration, we've observed a beat phenomenon. So this is the beat phenomenon just generated by the Coriolis force, and then of course we can sum all these results together due to the linearity of the equation of motion to give us the total response, which, again, since it's dominated by the Coriolis force, also reflects this beat phenomenon. So we found this to be very interesting, that there was the beat phenomenon occurring actually both in the first and second mode shapes. So we wanted to look a little bit more into this. Now, there's a professor at UCLA, a guy named Mark Fry, who hypothesizes that a large amount of strain generated by the gyroscopic forces really is one of the driving mechanisms in providing feedback for an insect during flight. And therefore, the beat phenomenon might also have kind of this same biological significance. It's our belief that the beat phenomenon may potentially be used to identify the yaw or other rotation amplitudes, and potentially be used as maybe a yaw rate sensor. Thus, it seems that if we're able to interpret this feedback in a way similar to an insect, we might be able to supplement traditional accelerometer or gyroscope-based control systems, perhaps with a strain-based control system, which of course might be smaller, lighter, more conducive to an actual microaero vehicle. But of course, there's a number of factors that could potentially affect the beat phenomenon, which would, of course, kind of destroy our null hypothesis. So we did a bit of a sensitivity analysis to see how sensitive this beat phenomenon was to a number of factors. I think there's more introduced in the conference paper, but today, due to time, I'll just talk about the effect of changing the yaw amplitude and introducing damping, which was neglected in the initial formulation. So the first thing we'd like to address in the sensitivity analysis is the yaw amplitude. And what we've done to basically look at the yaw amplitude is we fixed the pitch and the roll amplitudes according to the forward flight values that we presented earlier. We've then varied the yaw amplitude from about 0 to 0.3 radians, where the typical operation point in forward flight mentioned falls at about 0.2 radians. We've then gone ahead and solved the equation of motion, and then identified really how much each force constitutes the total response, or contributes to the total response, with the idea that if the Coriolis force, at least within the first mode, tends to dominate, then the beat phenomenon should be preserved. And as you can see, at the operation point, the Coriolis force is really constituting about 70% of this total contribution. And really, it's insensitive to small variations about this value. So if you were to increase the yaw amplitude or decrease the yaw amplitude slightly, you'd notice a pretty insignificant change in the overall contribution of the gyroscopic force. So a second factor we'll look at is damping. Now, the beat phenomenon is basically, like I mentioned, the interaction between the free vibration and the forced vibration of the wing. The forced vibration being that generated by the Coriolis force. So in general, structural damping tends to cause free vibration to die out over time, which, of course, based off of this formulation, would cause the beat phenomenon to die out over time as well. So really, to test this hypothesis, we've introduced a modal damping of about 1% and solved the equation of motion numerically, just to kind of see what result we got. And of course, you can see based off of this figure, the beat becomes indistinguishable within 1 second, which of course is problematic to our hypothesis. So we began asking ourselves, are there potential mechanisms by which the beat phenomenon could be preserved? And we found that there are. The first is basically randomizing these yaw rotation amplitudes about some mean value. And really, this is probably more reflective of actual insect flight. Of course, these aren't machines in nature, so they aren't going to have a perfect rotation amplitude every time. And by slightly randomizing this value, we found that we reintroduced the free vibration of the wing, and thereby we kind of maintain this beat phenomenon. And another way that this could potentially be maintained, or the free vibration could potentially be maintained, which again is not accounted for by our model, is quick translations of the insect body. So if the insect was to start and stop, basically the free vibration would be reintroduced, and that would cause the beat phenomenon to persist. So in biology, I guess this would lend itself to being beneficial for an insect to kind of moving around frequently, which you can kind of observe if you watch any flying insect. So the last component I'd like to talk about then is, of course, strain. Since strain is what we're ultimately selling here in terms of feedback mechanisms, I'd like to show how you demonstrate strain using this model. And so the strain from each different mode shape can be determined explicitly in finite element analysis. You'll notice this figure on the right is the strain for the first mode, both the two normal directions of strain and the in-plane shear. Then the total strain can be represented as a weighted sum of the modal responses, as indicated by this expression here. So for this this example, we're just considering these first two vibration modes. And then we have to select some point of interest to really figure out how the strain evolves as a function of time. And so we've basically selected a point near the base where the strain is the largest to see, again, how the strain changes with time. So this figure to the right then represents the strain as a function of time, and you can see that this also reflects a beat phenomenon. So basically, even though we're kind of looking at the contribution of two different mode shapes now with two different frequencies, the beat phenomenon is still maintained despite kind of the interaction of these two modes. You'll notice that the x and y components of shear are very small compared to the in-plane shear, which tells us a little bit about the directionality of the shear. So really, since this is the dominant component, the maximum direction of shear will be about 45 degrees from the positive x-axis. So with that, I'd like to briefly conclude this presentation, just summarize some of the results. That was an inertial elastic model of a rotating insect wing was developed with the following key characteristics. First, it was able to maintain a low number of degrees of freedom, which in this case was just the retained number of modes. So for our example, 2 mode shapes. It was capable of predicting the local strains such that it can facilitate studies in insect neurological feedback. Third, it was able to accommodate arbitrary geometry. You can all see that now we can kind of design any wing we'd like within the finite element software, so this can really constitute any insect. The major premise of the model was by treating it as a deformable wing, subject to 3-dimensional rotation about this fixed point. It was determined that the modal response was governed by Coriolis-Euler centrifugal forces, and that the Coriolis and centrifugal forces caused the beat phenomenon in the first and second modes, respectively. So lastly, we hypothesized that the beat phenomenon could potentially be used to facilitate strain-based control in flapping wing micro-air vehicles moving forth. We found that it was insensitive to small variations in the yaw amplitude. Of course, it does die out if you consider structurally damping, but again, there's various mechanisms that can be employed to basically reintroduce this beat phenomenon. And lastly, the physical strain from the first 2 modes also shows this beat phenomenon occurring. So I'd like to thank the National Science Foundation for supporting this work. I'd also like to thank my co-author, Dr. Steve Shen, who was unable to make it to the conference. And lastly, I'd like to thank the audience for your attention during my presentation. Thank you very much, and I'd like to open the floor to any questions.
So there must be many questions for Mark. We have time for a few of them. Rick.
Yes.
In the Delphi wing, when you compare the vacuum tests and the air test, we see that damping is very significant.
Sure.
The amplitudes in vacuum are much higher of the more flexible wing probably than the Hawkmoth. Do you think we can either incorporate that aerodynamic damping or aerodynamic forces? And how does that influence your
Well, that's a good question. I can't say, excuse me. The question was how do aerodynamic forces, or how can we possibly incorporate them into the model? Good summary? Cool. The answer is it's difficult to say. The reason that we've neglected it ultimately was there was some amount of experimental evidence in the past, an experiment where they actuated this in both helium and air, at least the Hawkmoth wing, and found that the deformation presumably was due to inertial elastic effects. So that's kind of the background as to why the assumption was made. In terms of actually implementing the aerodynamic effects in practice, again, that's not really my specialty. I'm not sure exactly how that would be done. We do plan to, while we validate this model, kind of do, again, a vacuum test in conjunction with an air and kind of look at these 2 results. And really, we think that the driving factor as to how valid this assumption is the different geometries of the wing. So certainly different insects might be dominated by aerodynamics, whereas some, like perhaps the Hawkmoth, are really a function or mostly dominated by these inertial elastic effects. But really, to answer your question, we're not entirely sure how aerodynamics will play into this, but we think there will be a number of other factors that really constitute the overall contribution of aerodynamics. Does that answer your question? Excellent.
Are there more questions?
Yes.
If I understood correctly, the mechanics is based on a linear bending model. Or you're taking into account the bending stiffness of the structure, but not the stretching.
Correct. Correct.
Now this is a membrane, and membranes are primarily dominated by in-plane stresses.
Sure.
Stretching. So how good is this model considering this geometry?
Sure. The question was, membranes are typically dominated by in-plane stresses. So how, since we're neglecting in-plane stretching, how accurate is our model? So the answer to that is, although in-plane stretching was neglected, you can actually still get in-plane strains. And the reason for that is because of the camber geometry. So if you imagine you have two fixed walls and a bent arch between them, if you push down on that, the overall in-plane shape does not extend. Yet you still are able to generate these in-plane strains. So again, we believe that the out-of-plane deformation will be more substantial than the in-plane, but that's the mechanism by which we're able to get in-plane strain without actually considering stretching of the wing. Does that answer your question? Excellent.
So one more short question, perhaps. So I have one, actually.
Sure.
So you show that this beat mechanism can lead to an estimation of the yaw rate.
Correct.
Do you see any mechanism for also estimating the other rates, pitch rate, roll rate, within the same principle?
So the question was, we've identified a mechanism by which we can identify the yaw rate, but can we extrapolate that to include the rate of, say, the pitch and the roll? The answer is not necessarily, not immediately, not based off of the analytics. There might be some clever mechanism by, say, system identification or some kind of more robust control algorithms, but just kind of looking at the form of the equation, from an analytics standpoint, it's not obvious how you would really extract those two rates.
Okay. Thank you. So let's thank the speaker.
Thank you.
Okay, so then I'd like to introduce the second speaker of this session. So his name is Ewout Smeur. He graduated in aerospace engineering very recently, I've heard. He currently is working on his PhD at the IMAV lab, and he's working on swarms of hybrid UAVs. So the floor is yours, Ewout.
Is it working? Yeah. All right. Well, thank you for all attending my presentation. So I will be presenting basically my master thesis research, which is about the modeling of a hybrid UAV using test flight data. So I'll first go through an outline of my presentation. I will start with a short introduction on hybrid aircraft. Then I will go into the quad shot, which I brought with me today. Then I will talk about the test flight campaign that was conducted, the modeling of the quad shot, results, verification of those results, and finally conclusions. So hybrid aircraft, they're not a new concept. They've been around for a long time. Right here we see the first one. And to quickly state the purpose of these aircraft, so they have vertical takeoff and landing capability, as well as fast forward flight mode, in which they can fly very far, so have a long range. So the last one you probably don't know, but these ones are very famous, of course, the Harrier and the Osprey. These are piloted aircraft, and in the UAV market, we see these systems only developing recently, because traditionally the UAV market is divided into these two concepts, the traditional fixed-wing aircraft and rotorcraft. And of course, the fixed-wing aircraft have the downside of that they need a runway or dedicated launch and landing systems, and the rotorcrafts have relatively low speed. So that's why we need hybrid UAVs. And the current status of these, here I give some examples of these systems. On the top left we see, well, something we cannot really call a micro aerial vehicle, but still it's hybrid. Though it still needs dedicated equipment for landing and takeoff. The other two don't. So we see the Mavion and the so the Mavion was also presented on this conference, as well as the Mavericks you might have seen. To the right, another concept which kind of resembles the quad shot, though it's only a two propeller setup. And of course, there are much more designs, all different. So now onto the quad shot. So it is a hybrid UAV. It has the four propellers like a quadrotor for stable hover. It also has flaps located on the bottom of the wing for better control of the roll axis in forward flight. And it runs paparazzi software, which is open source and available to everybody. And also the code that I developed for making this vehicle autonomous is open source. And here we see it both in the hovering condition as well as in forward flight. So for my master thesis, I developed a simple control scheme, which is so that the attitude control is controlled by a PID controller, and the outer loop guidance controller is based around that. So the attitude control is a manually tuned PID controller with gains that are scheduled based on the airspeed. So for forward flight, it has different gains as for the hover. And the guidance I made as follows. For the hover case, the altitude is controlled with the thrust, and the speeds are controlled with the attitude, which is basically thrust vectoring, just like a regular helicopter. And I made a function that aligns the quad shot with the wind, so it can make the most use of its wing. Then in forward flight, the altitude is controlled with the pitch, and the speed is controlled with the thrust, basically like a regular aircraft. And in between these modes, the guidance commands are interpolated, so that a smooth control is possible over the entire flight envelope. And this works reasonably well. But to improve this guidance controller, I wanted to have a model of the quad shot. And this model should incorporate the transition flight regime, because this is the most nonlinear part. So I wanted to have a longitudinal model to control forward flight velocity and altitude. And I decided to make this one piecewise linear. So I had 5 5 points in the flight envelope around which I made a linear model. And because wind tunnel time is expensive and it's usually a long waiting time, I decided to not do wind tunnel tests, but do test flights instead, and make the model that way. Though the quadshot has only low-cost sensors on board, so the challenge was to make a model using only low-cost sensors, and this can serve as a proof of concept for doing this on other vehicles as well. So the test flight campaign, inputs and outputs. I'm trying to model the airspeed, U and W. So the axis system is based on the hover condition, x-axis pointing forward and the z-axis pointing downward. So forward flight, the W will be negative, just a definition. The inputs for the model are thrust and pitch, and derived inputs are elephant deflection and pitch rate, which are used to control it. So what I did was I flew around with the quadshot autonomously while logging all sensors with a high-speed data logger. So to really see the vehicle dynamics, you have to excite the system, and this was done by doublet inputs. So doublet input is an input that goes up for a fixed time and then goes down for the same time. And this was done on the throttle or the pitch angle or both at the same time. And when this was only done on one input, the other input was held constant to make sure that it didn't have an effect on the modeling. So a doublet input on the thrust would look like this. And for the pitch doublets, an amplitude of 10 degrees was used, and for the thrust, an amplitude of 15% of hover thrust. So in the end, I did 9 test flights, and from these test flights, I got 91 doublet inputs. So it's basically flying back and forth between 2 waypoints and applying these doublet inputs for various pitch angles and flight speeds. So the sensor data was logged and processed on the ground. And of course, a state estimate was needed. For that, I made a extended Kalman filter with the following states: quaternion attitudes, body speeds, accelerometer biases, gyroscope biases, and the wind speeds. And using all the inputs that I had available on the quadshot: accelerometer, gyroscope, magnetometer, GPS. And I added a sensor boom, which is the stick here on the front, which has a pitot tube and a angle of attack sensor. And the result of the Kalman filter is shown here. So here you see 2 doublet inputs on the pitch angle. In the green you see the estimate from the paparazzi autopilot system, which uses a basic complementary filter. And in the blue, the output from the Kalman filter. So yeah, of course, it doesn't follow the reference perfectly. So there's some improvement possible. So the model structure is as follows. It's a longitudinal model, and I just consider the forces. So the force in the x and z direction. And of course, yeah, these equations are nonlinear. But since I make a piecewise linear model, I linearize those and then you get to these equations. And these should be valid for each moment in time. So if you so you can have one of these equations for every time sample, and if you then put them in a matrix, you can estimate the coefficients with a linear least squares parameter estimation. Now on to results. Here we see first some simple results. The trimmed pitch angle as a function of flight velocity. And all the different inputs are shown here. A circle is a doublet on both inputs. A plus is a pitch doublet, and an X is a thrust doublet. And you can clearly see that the more it pitches over, so this is 0 degrees and this is minus 90 degrees. The more it pitches over, the faster it goes, which is makes sense, of course. And here the throttle setting as a function of velocity. And we can see that there seems to be an optimum around 8 meters a second, though the mode controller characteristics are not taken into account here. So it would be interesting to make the same graph with a current sensor on board. Now, finally, the coefficients of the model, as I found them. The blue dots indicate coefficients if you only consider one doublet. But since I have so many doublets, I made 5 bins for the 5 models and calculated coefficients together. And then you get the red stars. And yeah, these coefficients, most of them make sense. For instance, XU indicates that if you have an increase in the U, then you get a negative acceleration. So which is basically, if you go faster, you have more drag. And here the coefficients for the z-axis. Now, I also try to verify these results. Here the model fit is shown. So in gray we see the accelerometer measurement. This is for the x-axis, and here I think a pitch doublet is shown. And for the y-axis, you can clearly see that the model fits quite well. Now, if you take it one step further and integrate the system, then we can integrate the accelerations and get the flight velocities. And I found that all the 5 models were stable. So then you can do this kind of simulations. So here it is compared. The blue line is the model, and the red line is the extended Kalman filter. And yeah, you can see that the estimation is not perfect. There are quite some oscillations there. But of course, yeah, only low-cost sensors have been used. So this is for the U velocity. For W, you get the following line. So this shows that the model is working. So the conclusion is that it is possible to obtain a model based on test flight data. So the coefficients were identified for a piecewise linear longitudinal model, and simulations shows sensible output. And for future research, I already using part of the model for the control I'm using now, but I want to do a full implementation of a controller based on the model. Other things that can be improved here are different input amplitudes for the modeling. Only pitch amplitudes of 10 degrees and thrust amplitudes of 15 degrees, 15% of the hover thrust are used. So a different range would make the model more accurate. It will also be interesting to not use low-cost sensors, but use high-grade sensors. Then I'm sure the quality will also improve. And the comparison with wind tunnel data would be nice. We saw earlier presentations, for instance, the Mavericks with a wind tunnel campaign. It would be interesting to compare that with test flight modeling. Other developments that I'm working on is changing the attitude control to an incremental NDI controller, and adding a velocity control loop to the guidance. And that is now working, which you could have seen on Wednesday, if you were there. And that basically concludes my presentation. Thank you for listening.
Are there questions for Ewout?
I'd like to ask, the data set that you use for comparing for verification,
yeah.
Is it a separate?
Yeah, it's a separate set. So those are not used for modeling. Yeah. Other questions? Yeah.
You would suggest more accurate sensors. Are they only needed for the more accurate modeling, or also in a later, say, production plane, would you need those more accurate sensors to fly well?
Good question. I think, the main sensor that was not so good was the GPS. You get a low update rate and not very accurate results from that. So I think just improving this sensor would make a lot of difference in both the modeling, but also in actual flight. Would it matter a lot? I'm not sure. For the modeling, yes, but for actual flight, you might not need the accuracy of this sensor.
You mentioned GPS, but
yeah.
I would think that GPS is the least important one because all your modeling is compared to air velocity.
Yeah, but in the Kalman filter, the wind speeds are estimated. So the GPS is an important part there. Yeah, also for the modeling, a better airspeed sensor would also be nice. But for low airspeeds, those are not very accurate. And of course, it's a directional sensor, and since the quad-shot flies at all different angles, yeah, it would be nice to have an airspeed sensor that could cover all these angles.
More questions?
Yeah.
Interesting. You say you're using the Kalman filter to estimate the wind?
Yeah.
But the wind is changing. How can you estimate the rate?
Well, yeah, so I'm also estimating a wind speed over time. So in the Kalman filter, the wind speed is allowed to change over time. But since you know that it will not change that fast, you can take that into account.
I also have a question. So I see that you added a very nice angle of attack sensor to the quad shot.
Yeah.
How did that work? I'm curious about that.
Well, it kind of worked, but not very well, since there is some resistance in the bearings, and I tried to calibrate it, but still the results were not very good, since only also low airspeeds, up to 15 meters a second. So yeah, it's not perfect.
So did you use it in the modeling?
I did use it, but I took into account that it was not very reliable.
In the Kalman filter?
Yeah.
Yeah.
Okay.
More questions for Ewout? No? Okay, then I would like to thank the speaker again.
Do I just use the laptop, or is there a thing to move the slides?
You can,
oh, that's right. Brilliant. Yep.
Okay, so I would like to introduce the third and final speaker of this session. So Sofia Armanini is the third speaker. She graduated last year at the Faculty of Aerospace Engineering at the Technical University of Munich last year. She currently is a first-year PhD student here in Delft, and she's working on system identification and the modeling of a flapping wing flight. And the topic of her research is the Delfly. So, Sophie, the floor is yours.
Right, thank you. So I'd like to talk about a set of flight tests we conducted with the Delfly, which is the flapping wing MAV developed here at the TU Delft. And the purpose of these tests was to determine trim curves and a number of other basic flight properties. And this was partly preliminary work for the modeling and system identification we're doing, and partly simply to investigate some of the properties of the Delfly. So, yeah, this is the basic outline I'll follow. So I'll start with a very quick introduction to flapping wing flight, and then say something about the experimental setup we used and the tests we conducted. Okay, so flapping wing flyers flap their wings to generate lift and thrust, and due to this particular mechanism, they possess a number of desirable flight properties. So they tend to be highly maneuverable and agile. They can typically hover, fly at very low speeds. Sometimes they can even fly backwards. And so, due to all of these favorable properties, there is currently a widespread interest in developing flapping wing MAVs. At the TU Delft, this type of research into flapping wing flight has led to the development of the Delfly, which I think most of you are probably familiar with, but for those who are not, this is the Delfly. It is modeled on a dragonfly, and its wings are arranged in an X configuration. Actually, several different types of slightly different Delflies exist, but the one that we used has a wingspan of 29 centimeters and weighs about 22 grams, and it is controlled by means of elevator and aileron deflections, as well as by means of the flapping frequency. So this was the subject of these tests. And the aim of these tests was, as I said, to quantify a number of steady-state flight properties. And this was yes, to quantify a number of steady-state flight properties to be used in current and future modeling and simulation work. And two particular applications we had in mind were firstly to contribute to ongoing work in system identification and modeling, which I'll say a bit more about in a moment, and also to allow for the development of simulation frameworks. Actually, at the moment, we have very little in the way of simulation for the Delphi, so this was also another application we envisaged. And in addition, on a more general level perhaps, the idea was also to obtain further insight into the flight testing of MAVs, which is still a relatively new field, so we hope to identify some of the important factors to keep in mind when flight testing such vehicles. So as I said, one of the purposes was to contribute and to aid current modeling and system identification work. And the reason for this is that at the moment we're using largely steady aerodynamic models and generally linear approaches. And so for these types of models, we need trim parameters. We need, for instance, to collect data around specific points. So we need to be able to conduct repeatable flight tests. And in order to obtain useful models that can actually be used, we also require trim points and trim parameters. So this was one of the main motivations behind these tests. Okay, so I'll say something about the experimental setup we used. The flight tests were conducted in the TU Delft Flight Arena, the Cyberzoo. The Cyberzoo is an optical motion tracking facility. It is equipped with 24 cameras that reconstruct the position and attitude of objects within the arena that are equipped with markers, with retroreflective or LED markers. And the tracking system can reach sub-millimeter precision and provides data at a frequency of up to 120 hertz. For this particular set of tests, we used LED markers, and these were affixed to the Delphi in the positions shown in the image. In addition to optical tracking data, we also required some form of control input measurement. And since the experimental setup we used and the number of LED markers didn't allow for accurate measurement of control surface deflections, we decided to instead use the commands given by the pilot by means of the transmitter. So that was the input measurement we used. And in a way, it could also be argued that effectively the pilot controls the command and not the deflection. So this type of formulation is also interesting in its own accord, although, of course, eventually we do want to consider the actual deflections. Okay, and before I go into the actual tests we conducted, these are a number of considerations we found it was useful to keep in mind when flight testing MAVs. And yeah, some of these we actually only found during the testing process. But so an obvious point is that MAVs by definition are very small and light, so any slight change to their structure can have a very significant effect on their flight properties. And this is especially a problem for fragile platforms like the Delphi, which are very easily damaged, even by standard maintenance or reparation work. And this can be a problem because it becomes difficult to compare the data gathered in separate flights. And along the same lines, attaching markers to a very small and light platform also affects or also can affect the flight behavior. So we can only use very small markers, which are less accurate, and we can only use limited numbers of markers. Finally, using optical tracking data, we have to ensure that the tracking performance is adequate, and there are several points to consider here, but one very obvious point is that actually the lighting conditions can have a very big effect and can lead to virtually useless data. So this is another point to keep in mind. And a very trivial point, but one that can have a significant effect, is the inherent limitation of size. So obviously a tracking chamber has a limited size, and in our case this meant that certain flight conditions couldn't be analyzed because there simply wasn't enough space and the vehicle would have crashed almost immediately. So these are some points that should be kept in mind. Right. The first test we conducted was aimed at determining longitudinal trim points, so trim conditions and the control inputs required to attain and maintain these conditions. And as a clarification, of course, a flapping wing vehicle, strictly speaking, is never in a steady condition. So what we mean is simply that in a flap average sense, it is in a steady condition. So it oscillates about a constant average. And we defined trimmed conditions in terms of pitch attitude and in-plane velocity. And the testing process, well, simply consisted in fixing the elevator at different deflections and using the throttle to maintain a steady condition and looking at the resulting flight conditions. Now, the main results we obtained are summarized here. These plots show the relationship between the elevator command and the resulting velocity and pitch attitude. And what we see is not unexpected. Of course, an upward deflection of the elevator leads to a higher pitch attitude and a lower flight velocity. But what we wanted to know was to quantify these relationships, which is what we did. And we also see that the relationships are approximately linear, although, of course, we would need further tests to corroborate this and to verify this. But we already have a relationship between control input and resulting conditions, which is one of the things we needed for our modeling work. And also, the obtained data provides, as we wanted, a relationship between steady state velocity and pitch attitude, and the obtained trimmed points are shown here. And again, of course, a high velocity implies a lower pitch attitude, which is as expected. The second set of tests consisted in evaluating steady turn behavior, and specifically we looked at the effect of different aileron deflections on the resulting turns, on the resulting turn radius and turn rate. And for this, we simply started in a particular steady flight condition and applied different aileron inputs, looked at the effect. And to determine the trim radius, we used a least squares approach to fit a circle to the measured flight trajectory, which we found worked quite well. And the results, again, as expected, a larger aileron input leads to tighter and quicker turns. However, in this case, we do still recognize a somewhat linear trend, but there is a lot of scatter. And partly this was due to problems we had in the testing process. We had some tracking problems, so the data was actually of quite a low quality. So there were some problems, and which is why for these tests in particular, we need further data to verify what we currently have. So the tests we conducted give us an overview of trim conditions and trim curves over a part of the flight envelope of the Delphi, and also an overview of steady turn behavior, as well as some experience and insight into the flight testing of MAVs. And the main utility, the main use we can make of these results is within modeling work that we're conducting. So as I said, these trim curves are particularly useful for linear modeling approaches. And also we can use this data to develop simulation frameworks. Of course, before we can do that, we need to collect more flight data and also to check that what we have now is actually right. And so that involves conducting more tests and in particular extending the current results to a larger part of the flight envelope if possible. And perhaps looking at further flight conditions such as climb and so on. And that brings me to the end. So thank you.
We have quite some time for questions, so go ahead. Erik-Jan.
Thank you for your presentation. I know there have been some other flight tests with the Delphi in the motion capture facility in the US.
Yep.
How do those results compare to your results from the site results?
Actually, the previous flights that were conducted with a different type of Delphi. So the comparison is a bit limited. Yes. So and also they were different types of tests. So most of them involved quick maneuvers. So maneuvers for system identification. So yeah, I'm not sure how much we can compare, but yeah.
When you're conducting the test, does it matter if the inputs are being done by flight controller or is it a pilot actually doing the inputs?
It's so in these tests it was a pilot. It was a manual input.
So
yeah.
will that make a difference when you're doing the modeling and plotting the results? Or does it really matter?
I think it wouldn't really matter, depending on how the autopilot works, of course. But if it's just used to apply the inputs, then it should basically lead to the same type of results.
More questions for Sophie? Guido.
What do they mainly use the results?
Yes. So as I mentioned, one use is within system identification work. So we used we did some work using linear models, which are valid only around certain points. And so to use these models, we need to know where these points are and how we obtain these points, and also to collect data for this. So that's one use. And of course, we can, as I said, we can also use the results for things like simulation frameworks. I think those are the main uses. Yeah.
So I have a question about the repeatability of the results that you got. So
yes.
Do you get the same trim curves when you test a different day, so the next day, or at different conditions?
Sometimes. So yeah, one of the problems, as I said, is that any slight change to the platform can have an effect. So if between two flights something happens, like a crash, or even some piece of the structure coming undone and being glued back on, so any little change can have an effect. So in that sense, we hope that results stay similar, but they do tend to change more than we want them to.
Did you do some kind of sensitivity analysis on this? So what failures cause the most differences in the trim curves? Or are you planning to do that?
We didn't systematically do that. So what we know is from just experience from flying. But yeah, I think that's something we could do.
But from experience, can you say something about this? So
I mean, the larger the change, the larger the effects. So of course, if the Delphi crashes and breaks into 5 pieces, then it tends to have a big effect. But yeah, so I think that's something we could look into more.
Okay, if there are no more questions, then let's thank the speaker again.
appreciate it for yourself.
Applaus for yourself. Okay. So before we start the session, so this is what this morning I mentioned, a small change to the program, or something that's different from your booklet. So we have this session now, and immediately afterwards we do award ceremony here. So because we can show some videos here and stuff like that of what happened during the competition. And after that there's a drink with snacks and stuff like that in the main hall. So after this session we stay here and do the award ceremony.
Okay, welcome ladies and gentlemen to the final session of this very nice conference. The session is entitled MAV Control, but actually it's not very much about control. So we have some fault estimation, we have some design, and we have some control in the end, swarming control. So let's start the session with Peng Lu. So Peng Lu will be the first presenter. And Peng got his BSc and master's degree from the Northwestern Polytechnical University in 2010 and 2012. And after that he came here to TU Delft to the Control and Simulation Division to do his PhD research on fault detection, isolation, and on fault-tolerant control. And today he will present his work about actuator fault detection and diagnosis for quadrotors. So Peng, the floor is yours.
Okay. Thank you, Eric, for the introduction. So, hello everyone. Now I'm going to present my work. The title is Actuator Fault Detection and Diagnosis for Quadrotors. So first we're going to start with a little bit motivation. So we are actually doing this for a reason, right? So for one thing, about the quadrotors, there may be some failures, right? Such as maybe your rotor may fail during the flight, and then it crashes. You don't want that, do you? So it may have happened in the competition. And also your motor may also not fail, and due to some other reasons such as wire collection and so on. And also, since you are using the battery, so your motor will also lose its effectiveness due to the battery consumption. So this is one thing. And for another, it can be used as a test bed. So you can use it to test some approaches, such as what I'm doing is fault detection and diagnosis for fixed wings, because sometimes it's difficult to test with fixed wings. Maybe here. So that's actually what I'm doing here. I'm doing that using this quadrotor to test some fault detection and diagnosis method for like fixed wing and other objects. So I'm going to give you a little bit background of this fault detection and diagnosis. About fault detection, the objective is to detect the fault. So maybe some faults can be observed, so, such as the loss of a rotor or your quadrotor. You can just see by eyes, but your system does not know what's happening. And maybe your controller will continuously give some insane control loss, which will kill your quadrotor. And that's why we're doing this fault detection, so that your system knows what is happening. There's a fault, so you need to take some actions. And then about fault diagnosis, the objective is to identify the faults. So you need to know the magnitude and also the location of the fault. Such as if one of the rotor fails or fails with loss of effectiveness fault, you need to know which one, because follow them. So this is a background for this fault detection and diagnosis. So you can see this is just a part of the command, and this fault detection and diagnosis system is here. It receives the information from the input and also the output from the sensors. And then it will Like if there is a fault, it will generate some fault alarm, and also it will have to tell the controller what the size of the fault, so the controller can take some actions so that your core rotor can still maintain the flight during or in the presence of this actuator force. So in this paper, we just consider about actuator force without a sensor fault. So we consider this nonlinear system with actuator fault. So this x, y, and just the state and the measurement, this f and h are just nonlinear functions of your system. This is a very general form. And this input fik is your input fault with your actuator fault. And this w, v, and other Gaussian noise. And then, since we are using a model-based fault detection diagnosis method for this approach, so we need to know the model of the quad rotor and also the actuator, and also we have to model the fault. So we come to the modeling part. Such as for Pratt Air drone and other kind of quad rotor, they have a general form of this system model. But this is actually a simplified model. As you can see, there many terms are neglected, such as hub force, and also hub moments are neglected. So this U is the total lift from all the rotors or your quad rotor, and this tau phi, tau theta, and tau q, tau psi are the torques generated by your rotors, or rather propellers. So for the measurement model, since we're doing the experiment indoor experiment, so we didn't use GPS, but we actually use this optic track camera system, which you can get relatively quite precise information about your positions. And we also use RMU, and this is a general form for this measurement model. It's just the states plus the measurement noise. So we have already given the model of the system. So now we have to also model the actuator, since we are considering the actuator faults. So this actuator model is just a simple low-pass filter. This is actually given by the company who made these quad rotors. And this small u is actually the input to your motors. And this big U is total lift. And if you split this small u into 4 different 4 inputs to your 4 motors, it can be written like this in this form. So we consider about the loss or effectiveness fault. So we give this loss or effectiveness factors to indicate the fault. So if there are no faults in these 4 parameters, this L1, L2, L3, and L4 should be equal to 0. But if there are faults, and then it's not equal to 0. If your rotor totally fell off, and then this L should be equal to 1, which means your rotor is gone. So we can furthermore write it in this form. So this paper is actually a continuous work or a previous work, which is I'm going to introduce you now. So this previous work is mainly about fault detection, and there we used a linear model. Since we just control the altitude of this quad rotor, so the dynamics should be very linear. So we just use linear control and a linear model, and also linear Kalman filter. So the work is, I can refer this work is give an introduction of this previous work. So the test is done by using this quad rotor, Q-ball X4 quad rotor, which is produced by a Canada company. So about the controller we used in this work is that we use the LQR controller. and the objective is to control the altitude. And we assume that the Euler angles are really small. Now, I didn't bring the video because I think you have already seen a lot of videos, and this one is not more special. So I just give you the result we have got. So this is the altitude command, and it's mirrored altitude. This blue line is the altitude command, as you can see. At about 15 seconds, the quadrotor takeoff, and then climb to command, climb to altitude, then it climbs again. But at this 50 seconds, there is a loss of effectiveness fault, which happens in all of the rotors. So your rotor, like this is a mirrored altitude, rotor just fell off, and then due to the controller, it can still maintain still track the command. So this is a result we get. And here we show the mirrored and the filtered altitude, since we use a common filter. So. And this is the result where the fault detection takes place. So we detect fault by using this residual. So if you give a threshold here, then you can know that at 50 seconds, around maybe 51 or 50, a little bit than 50 seconds, there is a fault happening in your system. So you know that your rotor is experiencing a fault. So there's a fault. You need to take some actions. But in this work, there's some problem. We didn't use a nonlinear model because we didn't consider about the position. We just consider about the altitude, which is quite linear. And also we use a linear filter. And also we just were only able to detect fault, but without we're not able to identify the fault, which means that we don't know how much the fault is. Then in this work, we just there are some improvements. We use a nonlinear model, and we also use a nonlinear filter, extended Kalman filter, and we also use then it's able to. We also try to identify the magnitude and the location of the faults. So I'm going to give you a little bit introduction of this extended Kalman filter. So you need first you have to predict the state and its covariance matrix. Then you have to calculate the Kalman gain. Then you have to use the measurement to update your state estimation and its covariance matrix. And since we are trying to identify the faults, so we need to estimate the faults. But first we have to model the faults. Because the fault is quite like a random walk, we don't know what kind of fault there will be. Otherwise, there's no need to detect faults. So here we use a random walk to model the fault, which means we don't know the dynamics of the fault. This is the modeling of the fault. Then we use this augmented extended Kalman filter. Then we can estimate the fault. And now we show the result. But now, currently, the result is only about simulation. We haven't done the experiment yet. So first, the first simulation is about there's without fault, actual fault. So this figure just shows you the position and altitude of the quadrotor. So we didn't control this position. We just control this altitude. So we give a command to the altitude, and then it tracks the command quite well. And also the Kalman filter also estimation. We'll see the estimation error here. This is a position estimation error, which is almost zero mean, and also you have a velocity estimation error, which is also quite small. And also as well as your altitude estimation, they're all zero mean, which means that your filter is working properly. And now we come to the fault estimation. So since there are no faults here in this simulation, So all the faults should be zero, and this filter takes some time, a little time to convert it to the real fault. So this is the result of without fault. Then we consider about this actuator fault. Here, so at 5 seconds, or maybe 6, all of the rotors experience a loss of effectiveness fault. The percentage is 50%, which means half your rotors maybe broke or something, or fell off, or something like that. And this result shows the fault estimation of the fault. Then this fault estimation is passed to your controller, so your controller knows what is happening. So there is fault, so maybe I should give like a bigger command or something like that. Then your controller is still able to track the command. So the tracking performance is a little bit like the situation without fault, so I didn't show it here. But of course, during the fault, there's a little bit spark. And so for the future plan, because this is we haven't finished this work, and we have to do a lot of things. So first, we're going to carry out this experiment. We have to detect and identify the actuator faults. And also, we will also have to consider both the position and both position and altitude. And we're going to also try with more complex maneuvers, which means that the controller may also be changed, but that's future work. So this is basically my work I've done, and that's all of my presentation, and thank you very much.
Any questions for Pang?
Yeah, yeah.
What about fault detection for sensors?
Just as I mentioned in the earlier. Okay, so your question is, I was talking about the fault detection of the actuators. What about the fault detection diagnosis for the sensors, right? As I mentioned earlier, this work I didn't consider about the sensor faults. Yeah, I just consider about the actuator fault. That may be considered in the future. Okay. That's a good question. Yeah.
I have a question for you. Okay. So on slide 16, you showed the threshold.
Yeah, the threshold.
Maybe you can show it again. So my question is, how do you determine this threshold? Because this is something you have to set beforehand. So how do you choose that?
Yeah, so to set this threshold is rather a little bit trial and error. But you can, such as at this point, this is without fault, but the residual is also not zero. So if there are no faults, you can perform some test before to test which this magnitude would be. Such there should be a bound for this value. It should not, if there are no faults, this threshold should be in a bound, not very big. So you can set a bound for this threshold, and then if it goes out of this bound, then you can detect the fault. So that's basically how you choose a threshold.
Okay, thank you.
Okay, thank you.
Any other questions? Yeah, one here.
Yeah, so thank you for the presentation. So can you go to sheet 38,
please?
8
or 28. Okay. That's almost, yeah.
What exactly do we see?
Oh yeah, this F1, F2, F3, and F4 actually the loss of effectiveness factor, which is L1, L2, and L3, and F.
So you're assuming a failure on all the 4 motors?
Yeah, all 4 motors. But at the beginning there are no failures, so it needs some time to convert it to the real fault.
It's still flying?
Yeah, it's flying in simulation. No, not in experiment. Okay.
Any last question? Yeah, at the front.
You mentioned that you were doing some testing using a camera system. Was default detection running on board, or was it running on a computer?
Can you repeat the question? Okay. So I talked about the fault detection or this actual fault. Did I perform it on board or off board, right? Actually, the test is done by one of the authors, not by me. I think maybe he's done it off board, but I'm not sure. Yeah. Okay.
Okay, let's thank the speaker again.
Let's see if it works.
This goes in your neck. Yeah. Like that.
Is it still? Yeah.
Yeah. Our next presenter is Dr. Nina Geisert. Dr. Geisert studied at the University of Stuttgart and at MIT from 2001 until 2007. After that, she obtained her PhD at the Max Planck Institute for biological cybernetics with Professor Bilthoff. And now she's working for Festo, where she is responsible for corporate bionic research. Nina, the floor is yours.
Thank you very much for the nice introduction. I'm very happy to be here today to present you the Emotion Spheres, a new design for human-friendly UAVs. And I briefly start with introducing the team. The two Mugrau brothers, they're very talented in making everything fly. The Jebens couple and Rabe are our IT specialists. Elias Knum is our project leader and a very talented designer, and I'm the biologist of the team, so I always do the biological background of the projects. So actually, unmanned aerial vehicles become more and more popular, and the civilian use grows steadily. Probably you all know about that. For example, here are some nice examples. The geologists collect data about ancient ruins. If you pass by a field, you do not see much if you just walk along, but if you fly over a field, you sometimes can see different patterns in the grass, and these patterns in the grass show you where the ancient ruins are. Biologists survey biodiversity. Mountain rescue detects avalanche victims, and actually we get great pictures from sporting events from the Olympic Games or so with unmanned aerial vehicles. However, the industrial use is still limited. Why is that so? Actually, first of all, if I want to use UAVs in an industrial environment, I have to perfectly ensure that there is no risk for humans. And actually this is a problem. If I think of a quadrocopter which is not functioning anymore and it falls down on a person, this is something that cannot happen in an industrial environment. Then the second thing is the limitation of flight time. And the third thing is, lots of you experienced that during the competition, the process stability and reliability, there are always cases of failure. So these are the three main reasons why unmanned aerial vehicles are not yet used that much in an industrial environment. However, I'm not from a research department of a university. I work for Festo. Festo is the global leader in automation technology and the world market leader in technical education. Our objective is maximum productivity and competitive strength for our customers in factory and process automation. So our team really wants to deal with issues in a production environment. Festo's main business is factory automation. This means that we handle objects. We pick and place objects and also fluids. So we have to know where these objects are, and if we pick the objects, we have to exactly measure the forces that we apply. We transport the objects, we have to measure the speed. And this is the reason why we look at nature, because all of these processes are optimized in nature for millions of years for energy efficiency and other optimization strategies. So for example, if you think of an elephant, the elephant wants to eat an apple, he has to exactly know where the elephant trunk is, where the apple is, and then as soon as it touches the apple, it has to exactly measure the forces that it can apply to not squash the apple, but instead to eat it. So all these processes, also like flying, are optimized in nature for energy efficiency, and this is why we look at nature to learn from nature. Actually, our team where we learn from nature is called the Bionic Learning Network, and here are some of our projects. For example, last year we showed a kangaroo, or here I already mentioned the elephant trunk. If you want to know more about that, please go to our website. Today I want to speak about the Bionic Copter. The Bionic Copter was inspired by a dragonfly. So actually, the Bionic Copter is a complex, ultralight, highly integrated flying object. Here you can see the role model, the dragonfly, and the dragonfly is really amazing. It can hover on the spot, but accelerate swiftly, go up, down, left, right, in all directions. And we built the Bionic Copter. And actually also our Bionic Copter can hover on the spot, but it can also accelerate swiftly, go forward, backward, left, right, up and down. So actually, why is that so? As for the natural role model, we can control the wings independently. We have one main brushless motor that actuates all 4 wings and makes them flap up and down. With this main motor, we can change the flapping frequency. But then each wing has one servo motor that we use to change the amplitude of the wing independently, and one servo motor to change the angle of attack independently. So in total we have 9 degrees of freedom. We have a wingspan of about 63 centimeters, a body length of 44 centimeters, a weight of 175 grams. And with that we can fly between 3 to 4 minutes. So, and actually when we built the Bionic Copter, we first looked at the natural role model, then we built our first prototype, then it did not really work perfectly, so we went back to the natural role model and back and forth. So that was an iterative process. And for example, we learned a lot about how dragonflies reduce vibrations during flight. But I want to focus on the wings now. The wings are very special. The dragonfly has a body length of 18 millimeters to 190 millimeters and a body weight of 0.2 gram on average, but a wing only weighs about 2 milligram. And actually, this is due to the fact that they're very, very thin. The dragonfly wing has a front edge, which has a thickness of about 220 micrometers. However, the back edge has a thickness of only 3 micrometers. And still with these wings, dragonflies can reach a maximum speed of 54 kilometers per hour and can even fly up to 1,000 kilometers on one flight. So when we built the Bionic Copter, we paid explicit attention to the wings. We built 7 different types of the wings and tested them. And what we learned is, as I already said, the front edge is way thicker for the dragonfly wings than the back edge. What is that for? Actually, the wing is kind of folded, but we can neglect that here. The most important thing is that we have a hard front frame and then a very thin foil that covers this frame. And actually it's just a flat surface, but as soon as the dragonfly flaps up and down with the wings, these wings form kind of like a sail of a sailing boat, or actually better, they form a profile like known for a helicopter. So here you can see that the tip is quite flexible, and so while flapping up and down, we have a passive formation of this wing profile. And this is essential for flying. And we took inspiration for that for designing the wings of our Bionic Copter. But actually, the Bionic Copter can only fly for like 3 to 4 minutes, and I spoke about industrial environment. With an industrial environment, we want to fly much longer. So we took inspiration from the wing design and built a propeller for a quadrocopter or something similar that is inspired by that design. we have a laser-sintered frame. So this is quite rigid, and this laser-sintered frame is then covered with a very thin translucent membrane. So as the rotors rotate in one direction, the membrane inflates into this direction and kind of forms a profile, but as soon as the rotor goes into the other direction, the membrane inflates into the other direction and forms a profile in the other direction. So due to this fact, I get a very lightweight but very strong or powerful propeller. So we generate 42 grams of thrust with these propellers. And the interesting thing is that I can have the thrust in both directions in exactly the same power. So actually, because they are so lightweight, I can also change the direction of rotation almost immediately without any latencies. So taken together, this interesting design makes a very human-friendly propeller. If I touch it, nothing will happen. And also, if the quadrocopter with these propellers flies against the wall, they do not really directly break off. They only deform a little bit, and then they go back in their normal orientation. Further, these propellers are very, very silent. So with these propellers, we first have quadrocopters or something like that are more human-friendly. But still it could happen that the quadrocopter does not work anymore, falls down and falls onto the head of a worker. So this is why we came up with the idea by combining an aerostat with a rotorcraft. So we took kind of the design of a quadrocopter or multicopter and combined it with an aerostat. Traditionally, aerostats are filled with hydrogen. However, hydrogen is very explosive. We cannot use that in a production environment. We can use superheated steam or hot air, but that cools down quite quickly, so also no long flight times. But we can also use helium. So far, helium was seldomly used because it's quite expensive. But we found a new 7-layer bidirectional PE/PP film, which is so thick, so dense, although it's only 25 micrometers thick, that almost no air leaks from that. So we built a shell with helium inside, and actually we fill it, and it stays totally dense for more than 5 days. So we only have to fill it once, and due to this, we can fly for a long time. Further, the helium carries my multicopter, and so the propellers only have to be switched on when they're really needed for positioning the flying object, but they're not needed for carrying the whole object. So because of this, the whole system becomes very energy efficient. And this is how one of the spheres looks like. We have 8 propellers, 4 horizontal propellers and 4 vertical propellers. And with this, I can move them up, down, left, right, up to 1 centimeters accuracy. In total, they have a diameter of 95 centimeters. This means with the helium inside, I can carry about 500 grams. And these 500 grams are almost exactly what I need for 4 LEDs, the EMU, the 12 processors on board, the radio unit for communication, my battery, and the connection for the charging station. So in total, it's actually it's almost fully balanced. The next step was that we wanted to move it in space, therefore we have to know where it is. And normally you do that with a Viking system, but a Viking system, first of all, is quite expensive, and it's actually very time-consuming to set up. So we built a new system with infrared cameras. Infrared cameras, because in an industrial environment you normally never have infrared light, so this makes it easy to install it and don't have any distractions from other light sources. The cameras are quite cheap and they're very easy to install. But the cameras that we used are point gray cameras. They don't have any infrared source. So the Viking system normally generates the infrared light, sends it to the object. On the object I have passive markers which reflect the light, and then the camera takes the picture. Instead, we use active markers on our objects. Because of this, we can cover a bigger space because the infrared light from the object has to only travel the distance between the object to the camera and not from the camera to the object and back to the camera. This means that with 10 cameras, we can cover a space of more than 30 to 30 meters. And actually, we can even use less cameras than 10, but we use 10 because we normally worked with 8 objects and we tried to avoid occlusions. So, if we have active markers on the objects, these active markers also need electricity to work. So if you would lit them the whole time, they would use a lot of energy. This is why we only light them up for about 250 seconds. Because of this, it becomes very energy efficient, and with the light patterns, I can also distinguish apart the different objects flying in the space and the orientation of the objects. So in total, with the camera system and the active markers, we have a cheap system. And actually, it's easy to install. We just take these cameras and we can kind of mount them wherever we want. And then we take one of our flying objects, our emotion spheres, with a defined marker cross for like 15 minutes. And we take pictures from all around. And by this, we can recalculate the position of the cameras. So you only have to put the camera somewhere, and then you have to fly around for 15 minutes. Then you have to like wait 3 to 4 minutes, and then the whole system is calibrated. So compared to the systems on the market, that is way quicker. So actually, the active markers send out the light, and the cameras communicate with the active markers via radio waves. So they are fully synchronized. The cameras only take a picture in the moment the infrared markers light up. And using these infrared markers, I then can distinguish the position of the objects. This position is then sent to a main computer. And on the main computer, I can implement different things. I can either have pre-programmed paths. With this, I can have the spheres fly in a choreography, or I can have stored behavior patterns so that they never bump into each other but avoid each other. Or I can also individually control them via the main computer or with a remote control. Further, the computer controls the energy status of each sphere, and when the energy status runs empty, it sends them autonomously to the charging station where they get recharged. So with this, I have a fully long-term stable system. So the helium holds for more than 5 days. The energy is recharged from time to time, so the spheres can stay in the air for several days without a human to interfere. And this is how it looks like. I know it's a marketing film, but still, you can see here are the propellers. They're very, very silent, and as I said, if a human touches them, nothing happens. So here are the spheres flying in our atrium, which is more than 30 to 30 meters. And either they fly in the choreography, then you also see that the propellers stop working when they are not needed. They are only rotating when they're used for positioning. Here are the cameras. Here are the active markers. And here is the charging station, was seen for a second. So, and here you can see when they run empty, they directly go to the charging station. They go on top of the charging station, rotate 90 degrees, and we have a ballonet fitting, so they attach to the charging station and then they refill their battery. And here you can see also that a human can directly touch them, nothing will happen. And for example, here you can see how the other spheres will avoid or react to the behavior of this one sphere. So, With the new propellers, we ensure safe human-machine interaction, and also the helium carries the object, so even if the propellers do not work anymore, they do not fall onto the ground, the spheres, they only very slowly sink down. We have flight time of several days due to the helium and due to the very energy-efficient propellers, and we have process safety due to the indoor GPS. And actually, where can we use that now? Actually, we can use it, for example, as a guidance system at a fair or in a museum. But what is also interesting for Festo, we can use it in a factory hall as attached or supplied with moving sensors. There are sensors in industry which are either very expensive, so that you do not want to buy 10 of them, or which have to be cleaned or adjusted regularly. So you can attach them to the emotion spheres, and then they fly around, collect the data, and then come back to get, for example, cleaned or set up again. Then also the camera system for us is really interesting, because with the active markers we can really span a big space, and we can track and position objects or small robots in the factory. And we can also track, if we want to, humans, and then avoid collisions between the humans and the machines. Thank you very much for your attention.
Are there any questions?
Okay.
So first, I would like to know if you have any, how much efficient is it the propellers, like I said, in noise reductions, any calculations or any you have? And second is, can you please highlight more about stored behavior patterns? And
Maybe we should do 2 questions first, and then the rest later. Yeah? Could you repeat the question?
Yes.
Thank you.
So the first question was if we have clear analysis on the noise reduction and the energy efficiency. So the thing is, as we are not a research department, but that we work for a company, we have very little time. So this whole project was done within 1 year. Also the bionic copter, from the first idea to the final presentation, was conducted within 1 year. So I'm a researcher and I would love to do more analysis on the whole stuff, but we mostly don't have that. The thing is, for the noise reduction, the emotion spheres are big balls. So if you attach a rotor to a big ball, you kind of have a resonant body, and this makes it very loud. So we had rotors, normal rotors at the beginning, and it was extremely loud. And then we had those rotors mounted to it, and there was almost nothing to hear anymore. So it was a significant reduction for our usage. And also, if you want to use them, you will hear that there's a big difference, but we don't have any clear analysis. I would love to do so, but we don't have the time in our department. For example, for the bionic copter, we are aiming to have them more robust, that we also can hand them out to some research departments, that they, after we presented them, do more analysis on the whole system. The second question was the swarm behavior patterns. So actually we tested different stuff. What you just saw was just a very simple rule. They do a random walk in space. The space has boundaries around, and the random walk is kind of like a Brownschen movement. And as soon as they get closer than 0.5 meter, they change the direction. So in that case, it's very simple.
Okay, your other questions? Yeah? Go on.
So that is like, I like to know more about the individually controlled behavior, and also about a bit of more explanation on the charging stations that you use for this sphere.
Yeah, so the question was more about the behavior there. Maybe we discuss that later, because then you can specify your question, because I'm not so sure what you directly mean. For the charging station, we use normal lithium-ion batteries, and then we kind of have only a ballonet fitting, which has the conductors, and we just attach it to each other, and that's very simple. I could send you the details for that, but that's kind of like just plugging it into your normal recharging station.
Any other questions? Koen.
Yeah, so did you look at disturbance rejection of spheres? So in a windy or turbulent environment?
So the question was if what happens with disturbances and wind. So the emotion spheres are totally not useful outside. So if we have some wind, that will not work out because the surface is just this big. But in our atrium and also in the production environment, we were able to control them up to an accuracy of 1 centimeter, and this was sufficient for what we needed. And we are trying to really get them into the production now. And then we have to test maybe if there are some areas where you maybe have hot air getting up, and then maybe the spheres have to avoid this region. But this is something that really has to be specified for the single case then.
What is the maximum payload that these spheres can carry?
So what is the maximum payload? The spheres have a diameter of 95 centimeters, and if you calculate how much helium is inside, the helium can carry about 500 grams. So all of our setup is almost these 500 grams, although we have some special LEDs and some additional stuff for marketing purposes. So in that case, we cannot really attach much more. But if we would increase the sphere by like 5 centimeters or so, you directly then can attach further sensors or so.
You made a new indoor localization system, which is energy efficient and probably pretty robust. Did you look at onboard, like non-external systems, and what grounds did you choose not to use it?
The question was why we used this setup for the external or indoor GPS system. First of all, we are working on further projects that might use the same system in the future. Then second, we really have the attempt to kind of use a Viken system in an industrial environment, but the Viken is really hard to use in an industrial environment because the setup takes so long. So this is why we decided to use this system, because it's way cheaper, and if we also want to sell this whole system, for example, to survey a whole workbench or something, then the cheaper cameras make more sense. Yeah. Yes.
So, did you look at onboard systems?
Yes. Why we did not use an onboard system? Because we also want to use the system for other stuff where we cannot use our onboard system. The thing is, we seldomly use onboard systems, because as soon as you have like fully autonomous flight with cameras or something, you directly get into the discussion of drones. And in Germany, getting anywhere close to military usage of these things is very bad communication. Festo is a family-owned business, and the family says we do not do anything with military. So this is for us the reason why we don't do it here, because also it would be possible to have the Baunicopter equipped with a camera, but then you directly get the discussion of can it be used to spy on someone, and this is nothing that we want to do with, or our communication department is totally against that. And actually this is a difference if you work in industry. You always have lots of people who also have an opinion on what you should do and how you should do it. And actually, yes, so as I said, the whole family owns the business, and it's a really cool family, and it's a really cool company, so we do what they say.
It's a very good answer. Any more questions? Yes.
One question on the Baunicopter, if I can. On your website and all the materials, you say that there are also some shape memory actuators. Do you actually use them for control, or is it just to make it cooler to turn its head?
So the question was if we used the electrical muscles in the Baunicopter. So the electrical muscles, for all of our projects, we try to test new technologies, and we want to see if these are really ready for the market yet, because then these technologies go into our research department and they try to make products out of that. And with the electrical muscles, this was also the question, are they already that far that we can use them for a suitable industrial application? So we used them. We first wanted to control or move the wings with the electrical muscles. That totally did not work out. Then we used the head and the tail, and that worked out because there the movement doesn't have to be that quick. So we always had issues with cooling down. The heating up was mostly quite quick, but the cooling down was always an issue. But then we also have to say, so the Bownicopter, when we built it, that was really a struggle. So probably most of you know that we crashed several times before we really made it to a stable flight. And there also these electrical muscles, they always, from crash to crash, they totally got destroyed. So in that sense, they were not really that helpful as we wanted them to be. But for the head and tail movement, it was sufficient, and that's why we used them there. Yes, so for the flight, we do not need the muscles. We need them for the head and the tail control, which is not necessary for a stable flight.
Any last question?
Yes. Thanks for the nice talk. I'd like to know how much I should pay to set up an infrared camera and stuff like that to measure X, Y, Z of just one sphere.
The question was how much the system costs to measure one sphere. And actually, this kind of a little bit depends on the setup. If you have a lot of obstacles in your area, but if there are no obstacles, 2 cameras are fully sufficient, and 1 camera is like 300 euro or something, then you have to buy our software, which is not too expensive these days. And then compared to the stuff on the market, it's maybe like 20% or so. 20% of what other systems would cost. But therefore, I would have to bring you in contact with the group working on the camera system.
One more question back there, yes?
How often do you need to calibrate your cameras? This is a unique calibration. And also, do you uniquely identify each balloon? Or is it just each balloon is the same thing?
So the first question was how often we have to calibrate the system. So if you mount the cameras to the walls or something and they're very tightly fixed, then you only have to calibrate it once, and that holds for tons of days. However, we showed it at the Hannover Fair, and we mounted it to little sticks into the air, and people leaned against it. And then kind of almost every time someone leans against one of these tights, you have to recalibrate it, what we actually did not do. So after like 2 to 3 days, we had an offset of like 2 to 3 centimeters. We always managed to still hit the charging station, but it was getting harder from day to day. The second question was the identification of each sphere, and actually we have 4 infrared markers per sphere that we always see at least 2 with at least 1 camera, and they flash up in patterns, and you can have different patterns per sphere. So due to the patterns of the infrared flashes, we can identify them apart. And yeah, the more patterns you come up with, the more spheres you can identify.
Okay, this was obviously very interesting because there were a lot of questions. And if there are any more questions, I'm sure you can talk to Nina later after the award ceremony. So let's thank the speaker again.
Thank you very much.
There's one already in there. Okay. Okay, the final presentation in this session, and actually the final presentation of the whole conference, is given by Christian Fuchs. Christian got his BSc in 2011 and his master's degree just very recently in 2014 here at the Delft University of Technology. And today he will be presenting his graduation work on an ecological approach to the supervisory control of UAV swarms. Christian, the floor is yours.
Yeah, thank you very much for the introduction, and good afternoon, everybody. It's nice to see that there are still some people around this late in the conference. So I want to change the pace now a little bit, because my work, even though it says control in here, focused more on the interface of a ground control station. So my presentation is outlined like that. I will first start with a brief introduction to the topic, then the work domain analysis that I performed, the improvements that I made, then I'll talk about the evaluation study that I performed, and I'll end with a couple of recommendations. So I'll just assume that everybody around here knows about UAV swarms and supervisory control, but who of you actually knows what ecological interface design is? Just a quick show of hands. Not that many, okay. So a quick introduction to what ecological interface design actually is. It was established in the early 90s, and the idea of EID is that you want to show what the work domain of a system is. That is the environment it is in and the system itself, so that you can then show how low-level information propagate up to the higher system goal. And then that way you just give the human operator the tools to understand what is going on, and you don't tell him what to do, you just let him do his thing, and as the human mind is quite brilliant, it most of the time works out. But to give you an example, let's just look at a car. And if you wanted to drive from this faculty to the cafe where we had the dinner last night, you could just give a set of instructions, like here. Not that readable, but that's not that important. You can follow them, you'll get there. Unless, of course, there's right about here on the Rotterdamse Weg, it's actually closed, and then you're stuck. Now, the ecological approach would be to show you what the work domain is. That is, give you a map, tell you where you are, where you need to go, what are all the streets, and then you can do your thing. If you then reach a closure around here, you just look at the map, take an alternative route, and you're done. So, but for that, obviously, you actually need to know what the streets are. And to get there, that is what we call the work domain analysis, which I'll talk about now. So the work domain analysis that I did focused on the following. I looked at 4 fixed-wing UAVs in a very generic surveillance mission. And I then performed that analysis, and I generated a tool called the abstraction hierarchy, which looks like that. You don't have to really go into all the detail here, that would take way too long. But the idea is that you have the purpose of what your system is, what you want to achieve, and you go down levels of abstraction until you end up at very low-level information, like, for example, the battery level. Now, to just prove that EID can be used for UAV swarms, we decided to just focus on a subset of this hierarchy, or let's clean it up a bit. Now, what we see here is the subset that we decided to use, and it includes an internal constraint in the form of the battery level and an external constraint, which is in this case the wind condition. And they propagate up through higher levels up to, in this case, the abstract function of coverage. So you want to survey an area, and that is your coverage. But how do then those low-level information propagate to that goal? It's not something that is easily recognizable by the human, so we thought it was a very good starting point to see if EID is applicable for this purpose. Now, the current interface that I was improving looks like this. The software we use is called Smart UAV, which is a research platform It was developed in-house here a couple of years ago that you can use to test various advanced control mechanisms, both for individual and multiple UAVs. It's similar to paparazzi, I would say. I also looked at paparazzi in the beginning, but for various reasons I decided to use this software suite. Now, looking at how well this interface already shows what I identified it should show, I would just look at the highest level that I identified, coverage. What you see is here, with those yellow lines, you see the past track of all UAVs, and you actually see like the future waypoints of the currently active or selected UAV. This does not tell you a lot about coverage, because what's the altitude of the UAVs? Kind of important if you want to know how much area you can cover with your sensor. And if we then go down, the function that I call the joint mission plan, that is how do the individual flight plans relate to each other? Well, you only see one. You can switch between UAVs and see all of them, but that leaves a lot of integrating to the operator again. And then going down, in terms of the remaining range, well, no information whatsoever. Also, the weather conditions aren't really represented that well. I do know that showing wind information is, for example, done in paparazzi, and very easy fix, actually, here. But when we look at the battery level, that's actually interesting. It's shown right about here, very tiny, and it's just a voltage. Given the nonlinear relation between the voltage of a battery and its remaining charge, you actually need a lot of experience to be able to tell how long you can still fly given a certain voltage of the battery. So now that I've shown my analysis and what the current interface is, let's look at what I actually improved. So the improved interface looks like that. It's still very much the same from the outline, but there are some crucial improvements, and I will go through a couple of them now. So the first one you will find right in this area with this huge white blob, you could call it. Now, with that, I represent the highest function of coverage. It's actually very easy. It's just a shading around the flight plan based on the altitude and your sensor. And it can either be a light shading that will show you predicted coverage, can be a darker shading that shows you how much you actually covered in the past. And if there's no shading, like here, it gives you information that you cannot reach that area. The next piece of improvement that I want to talk about is, again, found in the very same blob, and that is how the different flight plans and waypoints are colored. Now, I'm talking now about the function of the joint mission plan, so how do the individual flight plans relate to each other? What you see here is, first of all, actually all the flight plans, which is already an improvement, but then also different colors. If you just have a white color or black here because of the white background, it's fine. You can go there, you can come back, everything is fine. However, if you see a yellow color here, like this waypoint, you know that the UAV can reach that point, but it can't come back. It's then up to the operator to decide if you want to cover that area or you want to safely return to base. And red, well, obviously means that you cannot reach that point. Then two more improvements that I made that I'm not going to talk about too much. First, I added the option to show the remaining range at each waypoint as a function of the wind as well, and the wind itself. But much more interestingly is actually what I did here, which is a new state of charge indicator. Now, what you see here is, well, very basically, on the one hand, just the height of this column gives you the state of charge of the battery in percent. There's also a prediction in here that tells you how much energy you will have at future waypoints. I'll come back to that in just a minute. And two additional features. One is the current power consumption here with this ruler, and this black arrow over here. A small safety feature. It tells you how much energy you will use if you were to return back to base immediately. Now, about that prediction. There is a direct relation between all the waypoints on the map and these dashed lines in the state of charge indicator. It gives you a nice view of how the low-level information of the battery level or state of charge actually relates to a higher function, in this case the joint mission plan or even the coverage. For each waypoint, you will see how much energy is left when you reach that waypoint. You will see if you can actually return back, because the coloring scheme here is also with yellow. And there's even something as what I call negative energy, which tells you how much additional energy you would require to, for example, in this case, reach waypoint 7. Now, these are the improvements that I made. And now I want to briefly talk about the evaluation study that I performed to test if this new interface actually does help or if it was all in vain. Now, the study that I did, I performed in our ATM lab, which is basically a small lab with a couple of powerful computers and nice and big screens. There were 10 participants, and their task was to survey the town of Nootdorp, which is close by, still all just simulated. And then they were supposed to check for any problems and solve them, obviously. The data I gathered included a questionnaire, because I wanted to know how people actually use the interface. Also, usefulness ratings for all the individual improvements that I made. And I recorded the screen images and the voice of the participants and just told them to think aloud, because I wanted to really dive into their thought process. The scenarios that I tested are the following 5. They range from failures at individual UAVs or at all 4 UAVs. They also cover internal failures and external failures. 2 scenarios that I just want to point out. Scenario number 2 actually has no failure, dummy case. And scenario number 4, I designed to be unsolvable, just to see what happens if participants get a task that they simply can't solve. But speaking of solving, how did I expect participants to do this task? Well, this is a screenshot of the map part of the interface. You see here, this is the area that was supposed to be surveyed, and it's mostly fine, except for one UAV that apparently has some failure. Now, what I expected participants to do is first delete those waypoints that pose a problem, increase the altitude to the maximum of 500 meters, just the value I set so that there actually still is a problem in there, and move them around. Done. It's actually done within, well, it can be done within half a minute if you know what to expect, and it's all fine. Now, the results of the study. All in all, out of 40 individual runs that actually had a problem, remember there was 1 dummy case, 8 were not solved successfully. And out of those 8, there are actually 4 that failed due to some you might call stupid reasons. 1 participant forgot to actually upload the changed flight plan, another one forgot a small area in there, but failures nonetheless. Most notably though, scenario 4, the no-win scenario, was solved 6 out of 10 times. Now, what does that tell us? Well, on the one hand, I probably shouldn't design no-win scenarios, because apparently I'm very bad at it. But on the other hand, it also shows us that with this interface, people can actually employ very creative solution strategies that can help you solve problems that a fixed procedure cannot. Again, I'm the one who designed both the interface and the scenario, and I couldn't design them because I was so stuck in my way of thinking. Let somebody else do it, and it works. But now the question is, how did they do that? Let's have a look. There we go. So this is a very short video of one participant who actually did solve that unsolvable scenario. What you see here is that there's a lot of failures. And let me just play it. It's sped up by a factor of, I think, 4. So nobody was actually that fast. Still, what you see in the beginning, he removed all the bad waypoints, just as I expected in the beginning. Well, here are some bugs in the software, so it took him a bit longer. And then he goes about and just increases the altitude. Moves them around a bit. So far, nothing very special. But then, here we now actually go to one thing that I did not anticipate, moving those waypoints that were over here closer to the base. It actually is a very simple fix, yet I did not think about it. And with this little bit of creativity, you will see that in just, I don't know, another 10, 20 seconds, the problem is completely solved. Yeah, just a little bit missing there. Still a little bit hole over there. And done. Very easy, actually. So, additional results that I gathered. As I told you before, I also asked participants to give usefulness ratings to the individual interface elements. And these are the results. We can categorize them very easily. There are those that are very useful. Those include the predicted coverage and the coloring of waypoints and the lines between the waypoints. Then there are those that are kind of useful, which were in this case the state of charge indicators. And the rest, well, I shouldn't have done at all because they didn't use them. Now, let's just talk about a couple of those more surprising results in terms of usefulness. If we look at the predicted coverage and the waypoint coloring, so again, this shading and the colors here, I obviously expected people to find them very useful, otherwise I wouldn't have designed them. But I actually thought they were going to use them in a different way. The way I anticipated is that participants go ahead, look at the highest level of abstraction, that is the coverage, and see that something is wrong. And then dive deeper, try to figure out what's wrong. Actually, people didn't do that. They liked the colors much more. Turns out that putting some red color up on your face is much more efficient than just leaving out some obscure shading. The shading was still used, but not to detect the problem, but more to actually solve it, to make sure that the whole area is covered. Then next, the state of charge, both the current and the predicted state of charge. Now, those were kind of useful to participants. And they were only used in, or for two reasons. One, when people actually had the camera centered around the UVs or the base and not really the area they wanted to search, they used this coloring scheme to detect if there was something wrong. So instead of looking at the map because they hadn't centered it, oh, there's some red in the state of charge problem. The second one, which was used much more, is to just figure out which waypoint belongs to which UAV. In the current state, the waypoints all look the same, no matter which UAV they belong to, and then people try to correlate what they saw on the map with what they saw on the state of charge indicator. And then last but not least, the power consumption and the windsock. I haven't talked a lot about it before, but what I thought people would do is realize that there's a problem and then dive deep until they actually figure out what the problem is. And in all scenarios, they could have done that either by looking at the power consumption and realize that that is way too high for a single UAV, or look at the wind and realize that is way too strong for this whole mission. And yet it was never done. Instead, what people did was just solve problems at a very high level of abstraction. That actually is not a bad thing. It shows that this interface promotes skill and rule-based behavior, and you don't have to go deeper to find out what's wrong, you can solve it with very little effort, and that keeps mental resources free for other tasks. Now, to conclude my presentation, I would like to mention a few recommendations that I have based on my research. One is to actually differentiate the flight plans. As I told you just a minute ago, they look pretty much the same, and that gave some trouble to participants, especially in that unsolvable scenario where you have a lot of failures going on at once. There needs to be some way to actually directly see at least which UAV is the selected one. That was the number one feedback that I got. And considering that both the lines between the waypoints and the waypoints themselves were equally useful, one solution could be to not use the waypoint coloring itself for like the energy state, but instead use it to show which UAV is selected, and then only have the lines show that energy state. The second recommendation I would like to make is to also consider non-constant wind. In this research, I limited myself to constant and uniform wind to keep it a bit simpler. And now, if you want to make it more realistic, you obviously want to have a non-constant wind, but not just to make it more realistic, but also to try and force people to actually figure out what was wrong. If the wind is constantly changing and the prediction is thereby changing a lot, then you can force them to go down, figure out that it actually is the wind. I would be curious to see how that would actually change the usefulness ratings, for example. And last but not least, this was just a first step, a proof of concept. Can EID be used for UAV swarms? So the next logical step is then to expand it to include the full abstraction hierarchy that I generated. Specifically, I'd be interested in adding the quality of the measurements into the mix. Because for now, since you're only interested in how much area you can cover, you want to fly as high as possible and be done. But in reality, you obviously want to have a certain quality of your measurements, which is in direct contradiction to the coverage. So that would be really interesting both to find out a way to implement that and to actually see how people would then use it. Okay, that brings me to the end of my presentation. Thank you very much for your attention, and thank you for being here that late in this conference.
Are there any questions? Yes.
I have two questions. First is, for this, as you mentioned that we have the joint mission plan multiple UAVs. So is it limited just only for 2 UAVs, or it can be extended to n number of UAVs?
So the question is if this is only applicable to a set number of UAVs, or if you can extend it to any number of UAVs. I think that you can extend this to at least a couple more UAVs, but at some point it will be really hard, because in this case you have to manage each flight plan individually by moving the waypoints around, uploading them, changing them. So I don't know how many UAVs exactly you can control that way, but it will surely be less than 20, I would expect. Once you go to that many UAVs, you have to add additional forms of automation to get rid of that additional workload.
And second question is like, what algorithm have you used to differentiate between the waypoints of the multiple UAVs?
Could you repeat that, please?
Like, what algorithm have you used for differentiating the waypoints of the 2 UAVs for a joint mission?
So the question is what algorithm I use to differentiate the waypoints of the different UAVs. You mean how I actually selected where each UAV should fly in the beginning? I just did that by trial and error. I had the area that I wanted to survey, and I set out those flight plans by hand. And I gave those flight plans to the participants, and they just could use them to speed up the whole process. So the way that you actually lay them out in the beginning, you have to do yourself.
And what's that, can you approximate the area of coverage? What area of coverage you can estimate that you can calculate?
So if I got that right, your question is how I computed actually how much coverage you get from each waypoint.
Have you predetermined area of coverage, or it's been dynamically determined?
The way it works now is it simply takes the field of view of your sensor and then the altitude, and from there it simply calculates how much area that would be on the ground. It's not even very dynamic, so if the UV actually turns, that would not affect the coverage. In terms of if you can use more fancier algorithms to actually do that, I'm pretty sure you can, but I didn't in this case. Does that answer the question? Okay.
Yes, Rick.
You have a system that takes wind into account and you want to optimize range. The optimum flying speed when you fly in the wind is higher for range than when you fly with the wind. In which parts of your control strategy you would apply that?
So the question is, depending on whether you fly upwind or downwind, you would actually fly at different airspeeds for optimum range, and where that is implemented in this research right now, or where you would actually do it in the future?
Yes.
In the future? Okay. That is actually an interesting question, and I think I may remember you asking the same thing after my graduation. And to be honest, I am still not sure where you would do that best. You would, since this is now all done very manually, you would have to generate some automation advice. I'm really not sure where. The whole idea here is that you don't generate an advice for the operator. You just show what he can do and let him do that. So I'm pretty sure it's possible and it would be interesting to do, but I don't know about it. I'm sorry. Maybe.
Yeah. Question at the front.
What kind of inspiration has you used to design this ecological interface? Are you doing this from the point of view of the pilot, of the mission manager, or of a air traffic controller, for example?
So the question is whether I looked at this more from the perspective of a pilot, the guy in charge of the mission, or more an air traffic controller. In this case, it would be, I would say, more like the one in charge of the actual mission, just because this is not applicable for a safety pilot, because there you still have to have a one-to-one relation, and here it's actually one operator and many UAVs. So in that case, it would be the mission operator. Does that answer your question?
Any more questions? Yeah, Koen?
How much training did the participants receive before being able to do your experiment?
The training was a little bit over an hour. So it started off with just a very basic introduction into smart UAV, how you can actually change waypoints, and then it moved on to what you can do with my improvements. So that in total, about an hour, maybe an hour and 15 minutes, but people were actually quite confident about using the interface after that.
They were fully trained after that period?
I'm not sure about the term fully trained, but they were trained enough that I did not see any significant improvement in their performance throughout the next 5 trials that we did.
Yes?
Have you tried that the participants are using the old interface, or you just use the new one?
So the question is whether I also had the participants use the old interface versus the new one. No, I did not. We decided that it would be a very unfair comparison, since the original interface was not really designed to support multiple UAVs. And in that case, we thought it's going to show that the new one is better, but that's so obvious that we'd rather just look more into how exactly people would use the new interface.
Any more questions? Then let's thank the speaker again. So this concludes the final session. I would like to ask you all to remain seated because we go straight ahead with the award ceremony.
For those who would like a little pit stop in the restroom, you can still do that. It will not go that quickly. So. So before we go to the award ceremony, actually we would like to give the chance to Professor Moorman, who will be organizing the IMAV next year, to already give you a little bit of taste of next year.
Thank you very much. So I know that just short before the ceremony, there will be all attention now in the room, and so that's the correct time for announcing the next IMAV 2015, which will take place in Aachen. You just see a picture of the dome of Aachen. The conference will most likely be from September 8th to the 11th in 2015. And if you just skip to the next slide, please. So just a short view on where Aachen is. In fact, not too far away from Delft. So what are we going to do? What is going to change? So just some minor points. The first point is that we will basically keep everything as it is. So the IMAV is a well-organized and well-thought-about event. So we will basically keep it. A little change will be with respect to flight competition. So as there has been before, there will be an indoor and a dedicated outdoor session. The outdoor session will most likely to be some fire detection, firefighting scenario to be further detailed within the next week. And another thing is that besides surveillance recognition, which is a focus on this IMAV and IMAVs before, there is put an additional focus on air vehicle design, so to encourage people to do new designs, improve design methods shall be an explicit deal to improve performance and endurance of the system, and that it will also be considered in the scoring at that time. Another thing, there was a lot of discussions before also with some of your visitors here, competitors can try to do complete missions, but it's also very much appreciated within the IMAV group if you just focus on one special mission element and do something very particular. So don't hesitate if you say, oh, the complete mission, I cannot perform it. If you just can do one thing, please come and show this in an excellent way. So this is one of the scopes. So at the end, hope to see all of you again next year, September 8th to the 11th in Aachen. So looking forward to seeing you. Save the date.
So indeed, we hope to see many of you next year again. We ourselves are not going to go, but if you go, that's fine. So, yeah, now the most exciting part, and we start with the most important things, which we also denoted as the boring part. No, we would like to thank a lot of people, and first we would like to thank the sponsors who made this event possible. So I think it was very, a nice event with nice food, nice locations, and all these things, things going professionally. This is all thanks to the support we had from the organizations you see on the flags to the left there. So we would like to ask them to come forward, and so that we can thank them in person and give them a little gift. And they would also like to say something to you very shortly. Please give them a warm applause. Thank you very much. Aerialtronics, yeah. I just noticed we have a shortage of umbrellas, so we give you one, and then you need to cuddle together when it's raining. And but if you would like to say something to the audience.
Yeah, sure. Thanks all of you for coming. Thanks for participating in a wonderful IMAV. We were very excited to see all your contributions, and Yeah, it's cool to see that IMAV is so close to practical applications. We're a very young company focusing on those practical applications in as a real business. We've been going for 3 years now with Aerialtronics, and we grew from 2 to 40 people. So we're growing really fast, and every day is warp speed at our office. You all are very welcome to try your hand at the real stuff in a commercial environment. Really, within the next years, we're growing so rapidly that basically anyone in this room looking for a job is very welcome to join us. Thank you so much.
We would also like to thank the people from Parrot who have been supporting teams with AR drones. So you make them better and better, and then we use your technology and we claim the prizes here at the competition. And that's how it goes. So thank you very much. You also... Yeah, and if you would like to say something to the people here, you're welcome.
Yeah, we're also very happy to have you here. It's always a pleasure to see everyone's work, which can be really inspiring, and some new stuff like flapping wings, for instance, which is quite new for us. Yeah, very inspiring, and well, I hope I will see you in Aachen next year. Thank you very much.
Also thanks to you. So, and then 1 bit squared, yeah, well, Piotr, your name is not 1 bit squared, but thank you also a lot. And also for you an umbrella. I hear you stay another day or 2, so you may need it. So if you could, if you want to say something.
Yeah, thank you very much, guys. It was a pleasure to be part of this, and I'm glad that to see how the progress goes on. It's like I've been following and being part of this for quite a while now, and just seeing how far this autonomous systems are getting is just mind-blowing. It's great. Keep up the great work, and I can't wait to see the progress you will make over the next year. On the next IMAV, I want to see what you guys can come up with. You're brilliant, and thank you very much.
You're brilliant too. Anyway, so and then I would like to thank our friends from the Dutch police for keeping us all safe, of course, during the event and during the day. But thank you very much for your support. Already for multiple years. Thank you. I also give to you an umbrella. You must have one already, but would you like to say some words?
Well, we were impressed about all the knowledge and all the new techniques you brought, and you looked and gave us a look this week, and we were looking forward for the next years. And well, you said it already, keep on the good work, because we were impressed this week. Thank you very much.
And then our friends from MathWorks. Many of you have MathWorks caps and T-shirts. So all together we pitched in some coins and we bought you 1 umbrella. So thank you very much. And if you would like to say some words to the teams, some you supported.
Sure. All right. So first of all, it's a real honor to be here, and we're really grateful of all the hard work you guys put in. We noticed there's some moments of stress, but I don't believe an IMAV would be fun without any moments of stress. But the good news is you guys pulled through. It was really cool to see what you did. We're very grateful that you guys use our tools, and we gave you the free software, so that's one thing. But the realistic part is, free software or not, what we really would like to do is for you guys to engage with us, talk to us. If you need help, use us as a resource. So more than just giving the hats and the T-shirts, there's a whole bunch of people just like yourselves who have graduated, joined the company, which are more than willing to help out and help you solve problems if you need it. So feel free to reach out. And what else to say, but thanks for all the good work and keep going.
And John Preston from UZaitka, thank you very much again for your support, also from ONRG. And yeah, if you would like to say some words, we would be happy.
Okay. Just they've pretty much said all previously. Would like to say it's great seeing all the diversity and all the creativity. Much appreciated.
Guys, thank you very much. Three people we would also really like to thank are the three keynote speakers who have given some really inspiring talks for different reasons with different platforms. So Sawyer, Eric and Petter, if you could please come up here, then we can also give you... Wil jij het doen of geven of zeggen? Ik zal hem geven. Ja, okay. Geef jij de paraplu's? So, Eric, thanks a lot for coming here. It was really inspiring, and we're definitely going to implement this time adaptive control. Petter also, really thanks a lot for your talk. Many people have been talking about it yesterday and today, and I hope we see you again sometime at an IMAV. Thanks. And Sawyer, also thanks to you. Keep on going with the RoboBee, and if you have it flying with battery, yeah, send us the video before you send it to the rest of the world. Then we can copy it. Thanks a lot. Okay, and now to the official prizes, and we start. Okay, I'm mixing up the order. We practiced this many times. Anyway, so we start with a little video. So last years we had a lot of difficulty to find some images of the drones and make a nice video. Like we had 5 seconds, 3 seconds, 2 seconds, and then we had to make a video. This year we had so much help from the police and people filming it, and Aerialtronics filming it from above, that we had a team of 3, 4, 5 students looking at all the hours of material and try to condense it into a small video of the competitions. It has lots of images that you did not see because you were standing far away, and I hope you enjoy. Now, watching this video made me remember one thing I completely forgot. I saw all these people running. I was like, that's not me. And it's actually our helpers. And our helpers, yeah, their name signifies that they helped us really a lot. And yeah, actually we could not have done without them. They've been solving some really mean, tough issues, like the live streaming on Friday evening at 10 o'clock. They were completely destroying and then putting together again the streaming system here in the lecture room. They have been arranging a lot of things, helping you guys out. So I would like to invite them up front, everybody that has been helping the last few days, because I think they really deserve a warm applause before we go to the award ceremony. So could you please come forward and... So guys, thank you very, very much. Last times that we organized this, we were completely destroyed after this week, and now you are completely destroyed, but we are feeling actually pretty good. So thanks a lot, and yeah, please give them another applause, and yeah. You may be expecting a present now, but you will get something later. Actually, because you have to arrange now. We will arrange something for you. So thanks very much, and yeah, really, yeah. But okay, we will get emotional afterwards. Okay, thanks. Another applause. Thanks. That's it. If people need to get trains, planes, no. Can we? So we start with the best paper award, and this gave us a lot of headaches because there's actually some really very nice papers that have been presented, and well, since I'm already taking much too much time, let's get to it. The committee that was judging this used also the reviews, and it's from Mark Jankowski. So, yeah, congratulations. What the committee really appreciated was the original thought that you could perhaps tell things about the yaw control of the tension in the wings. That idea alone is very nice. And the way in which you studied it by decomposing into like Euler, centrifugal and Coriolis forces, we thought it was a very original approach. We would stimulate you to test it for real, but that's the only remark we could make. And I would really like to congratulate you. You get this beautiful gift. It's the prize. And oh yeah, picture moment. It's a picture moment actually. What are the helpers doing? They're relaxing. You should take pictures. No, congratulations. And last but not least, you get this Lisa S kit. So it has everything. It has the little ladybird, the Lisa S. It has all the cables you might need. So yeah, it's
start playing with it. Everything is inside, so you can start testing with it.
So congratulations, and yeah, we hope to see you in the future. Thank you very much. Congratulations. Now I would like to pass on. Oh, sorry, no, yeah, okay. And then the special achievement, which was also hard to pick because there were so many special achievements. We even had a bike crash this year, and we were thinking about that. But that's not nice. Huh? Anyway, what we picked was the following: was a team that kept persisting, like it kept persisting at what they're doing, and I think now they're very, very close to something really great. We want to encourage them, like reward them for the hard work they did, and encourage them to go even further. and that's for the Mavericks team. And so if you could please come down. As you may or may not know, they try to control this almost impossible to control tilt wing, and they put a lot of hard work, analysis into it. And this year, I must say, was looking pretty good. And so, yeah, we would like to congratulate you and give you this Special Achievement Award. Congratulations. And also for you guys, Lisa S. Kit, but you have to fight over it. Or play together, that's better, sorry. You play together with it. Okay, thank you. Yeah, now behind. Okay, so now, before the final ranking, I would like to give the word to Christophe de Wachter, who was the head judge, and he will go into some of the scoring details so that you know what was happening behind the scenes.
Yeah, thank you, Guido. Head judge, so that probably means you'll all be mad at me. The head jury, so you'll, so I'm the one to blame. We try to be as fair as possible. Let me recap a little bit the spirit of the rules. So imagine there's a big, major scenario, a huge amount of land is collapsed, roads are stuck. So we wanted you to develop a lot of automatic machines who could help in research and rescue efforts, and that's why the more vehicles you had and the more autonomous, the less operators were actually needed to operate them. That's when these vehicles will actually be useful. And the rules were just like that. If you're, for instance, a vehicle could take off properly but did not help in this mission, did not score any points and retrieve a nice image or anything. Unfortunately, we had to be very strict. It was written in the rules that only the successful flights were taken. So I would like to show you some footage of the teams. You probably know what your team gave to the jury, but maybe it's nice to see what others have shown, so you get a better feeling of where we are. Very quickly, and I won't mention whose picture is what. So if you absolutely want everybody to know, you can yell, but otherwise, so here we go. So you see the blockade, maybe? Maybe you have to dim the lights. Nog langer? Well, let's just go on. One blockade, hard to see, but all kinds of images. Some stitches are pretty lonely, so like a single image stitch, but they still get the thing. Some stitches are pretty nice, but only part of the village. Very well done, nice job. We were amazed by many of them. Some were really good, but inverted or mirrored. Some were smaller, but had just the thing that they needed. Some were a little offset. Some were interesting. Some were a little dark, but very special on board, so they were very amazed. The rectangle is the calibration square we had in the field to measure the resolution. And the red circles are for the obstacles that were detected. Some were actually really useful. Imagine you're a rescue worker and you get this map. I believe in less than 10 minutes. That's why we were very annoying. We didn't give you a lot of time. But we want to know as fast as possible where you can ride and where you can't. So yeah, you could do a very fancy stitch, but these maps were actually generated within competition time. So this is really useful. This is a close-up of the calibration pattern. We hoped you could see the very tiny little thing in the corner, but that's... do we have a beamer? A pointer? No. Well, there was a 30 by 30 centimeter thingy over here. Is this mirrored? Yes, it is. There was like a smaller one here, and nobody actually got us a clear picture of the very small one, 2 centimeter one. but still very amazing considering the size of the vehicle. Many people do this with much heavier platforms, so that's an achievement of its own. Another stitch, another close-up resolution image. Several teams attempted to read the digit. Here's an example of, I believe, what should have happened. So to automatically recognize the number. Here's an example from another team of a lot of pictures from indoors, seeing all kinds of obstacles, chairs, and stuff like that. A lot of people also flying on FPV with house numbers, a lot of automatic house number recognition attempts as well. So thank you for all these efforts. We really see an advance, more computer vision, more autonomous flight, more the things that we want to see. So thank you for developing them, and hope this encourages you to do the same next year. This is where I believe one of those attempts to fly in goes from left to right. So, ta-da. After filling out everything in the Excel sheet, the magic huge Excel sheet, it took many hours to fill it in, but there was a very clear ranking. No doubts. Everything was very crystal clear. Yes? Yeah. Well, sorry, I didn't have enough sleep. Can we stop the live streaming?
Who typed this?
I have too many copies of this, so they will all be wrong. Guido.
No, you can do it.
From third place on to, well, you don't have to pay anything. We'll give you the other prize. In the third place of the IMAV 2014 competition goes to IMAV. IMAV.
Congratulations.
They lost a bus, a van, but they won this plastic thingy. So congratulations. Are you adapting prize to prize? He is. Perfectionist.
Who said anything? So, the second place of IMAV 2014.
Yeah, you can. Yeah.
Well.
Stay.
You can please stay so we can have a large picture. So, Enak, thank you. The things you did especially well is the map stitching. You had definitely the most useful map of all teams of the entire village at the highest resolution. Read the digits and all kinds of things I forgot now, but it's in the Excel sheet. And the picture as a third prize. The second prize for this IMAV competition goes to Team Depot. Team Depot. Team Depot participated with 3 vehicles. 3 vehicles at the same time. They had an autonomous stitching, and they had a very, very talented pilot who flew, we couldn't count, but up to 19 times through windows, doors, and stuff at such a rate that we probably even missed several, recognized all the houses that were within video range, not once, but twice, just to be sure. And we only counted for every new room 1 point, so every room he went through 7 times, we counted only as 1. He should have picked another building, then he would have. So we think that the score is fair, but very well done. Congratulations on your second prize.
He wants to thank his team notes in the live stream.
I would like to thank my 2 pilots. They are on the internet. We have the trophy.
So, last but not least, who can guess? Who can guess? First prize to Singapore! Congratulations for National University of Singapore. Singapore came with an amazing team. I even lost count how many UAVs, how many MAVs you actually brought, which is a total amount of UAVs. Wasn't it like 10? So every 5 and then a backup for everyone. And they did a lot of very autonomous demonstrations. They had vision-based precision landing on the roof with target recognition. They prepared the 7-segment display recognition. They did amazing job indoors, which got them a lot of points. Autonomous flying from one room to another. Yeah. So the autonomous flying from one room to another was fantastic. Not everything worked out as they wanted, so otherwise they would have had even more points. But very big team and amazing performance. Thank you for showing all this nice work to us.
So, congratulations, oh my God. I'm going to sleep this weekend. So congratulations to all of you again. You could go back to your places, and there's still 1 prize and 1 remark. So, and there's some confusion about the name of this prize. Because when I read it, it says worst crash. And there were quite some crashes. And it would be hard to pick the worst. Bart just told me it's the prize for the best crash. There's something to say for that as well. But actually I think it should be the prize for the most persisting person. And yeah, it's somebody who has spent, oh, he's trying to run away now? No. It's somebody who spent his summer here, working day and night on something that nobody has done before. Very small flapping wing to fly autonomously outside on GPS. He came here, he's French, but now he speaks also a bit of Dutch, which is pretty amazing. And he got to learn to ride a bike. And typically he does it very well, but on the day of the competition he has a bike with very small wheels and strange control properties. So still, yeah, Clément, we would like not only to thank you for your as a helper, but we would also like to reward you for the best or the worst crash. From what viewpoint you see it? Thank you. He's a tough guy. He's a tough guy. He was all bleeding and stuff. Very good. Thank you. So, yeah, next year, IMAV 2015 in Germany. You may have seen these T-shirts. They were designed by the student helpers. It says it's not a bug, it's an MAV. And we have been wearing them. And we have absolutely no use for them anymore. So if you're leaving and you think like, oh, I would like to have such a T-shirt, then you can take it. We put them here. Don't take the Lisa S. Don't take this drone. Just the T-shirts. So thank you very much for being here. We've really enjoyed it. We've seen many interesting things. And after the conference, what we will do is we will make the video perhaps even more interesting, a bit shorter. We will put stuff online, and there's all the presentations. So, for example, this morning when some of you, only a few, were sleeping, there were some presentations. If you want to see them again, you can by going to the recorded videos. Thank you very much. Oh, I'm so stupid. Sorry. So there's actually a drink still. So of course, those of you who have to leave, have a safe trip. For those that would like to perhaps still talk to some people, there's a drink here with some snacks. So thanks again and enjoy.
No, I'm just asking who wins the big quadcopter.
Oh, really? Nee?